The surface of the open ocean is bright, wind-rippled and restless, but beneath it lies a world where vision dissolves and sound becomes architecture. As the camera follows a massive body slipping below the waves, light fades in gradients of blue that darken into ink. Within minutes, the world becomes nearly lightless, and sight loses its authority. It is here, in this descending corridor, between the sunlit surface and the true abyss, that the sperm whale begins to operate not as a creature of sight, but as an acoustic strategist. The deep ocean is not silent. It is structured by vibration, pressure shifts, distant tectonic murmurs, and the faint crackle of biological movement. In this environment, the sperm whale does not peer into darkness. It listens to it, and more importantly, it shapes it. The head of the sperm whale is not simply large. It is a specialized acoustic engine. Nearly a third of its body is devoted to a structure called the spermaceti organ, a complex arrangement of waxy oils and connective tissues that focus and amplify sound. From within this vast chamber, bursts of sound are produced. Sharp, concentrated clicks that can reach intensities unmatched in the animal kingdom. Each click travels outward through the water as a tightly directed pulse. When the pulse strikes an object, a squid's mantle, a drifting fish, the uneven contour of a thermal layer, it rebounds as an echo. Those returning echoes are not random noise, they are data. Through subtle differences in timing, intensity, and frequency shift, the whale reconstructs a three-dimensional map of its surroundings. Distance is measured in fractions of seconds between emission and return. Texture is inferred from how sound scatters. Movement is detected through Doppler shifts as prey shifts position. In simple terms, sound pulses leave the whale, bounce off hidden objects, and return carrying spatial information. In practice, it is an acoustic vision system so refined that in absolute darkness, the whale can distinguish prey from debris with astonishing precision. At depths where sunlight cannot penetrate, this sensory adaptation is not an advantage, but a necessity. Eyes remain useful during the initial descent, when faint residual light still silhouettes descending forms, but beyond a certain depth, the retina receives little meaningful input. Many deep-sea organisms respond to this darkness by producing their own light, bioluminescent flashes that flicker like distant signals. Yet even these signals are sparse and unpredictable. Prey in the deep ocean is not concentrated in herds that can be chased across open plains of water. It is scattered, dispersed across enormous volumes of near-empty space. For a predator of this scale, the challenge is not speed, but detection efficiency. The sperm whale must search vast three-dimensional expanses in which potential prey items are separated by tens or hundreds of meters. Every dive is therefore a calculated expedition into scarcity. As the whale descends past a depth where pressure rises dramatically, the physical environment becomes hostile. With each increment of depth, hydrostatic pressure increases, compressing air-filled spaces and demanding physiological compensation. The sperm whale does not carry air in the way terrestrial mammals do during extreme depth excursions. Its ribcage is flexible, allowing the lungs to collapse safely under pressure, minimizing nitrogen absorption and reducing the risk of decompression injury. Oxygen for the dive is not stored primarily in the lungs but in the blood and muscles. The whale's blood contains high concentrations of hemoglobin, and its muscle tissues are saturated with myoglobin, a protein that binds oxygen efficiently and releases it slowly during exertion. Before a dive, the whale performs a series of deep breaths at the surface, replenishing oxygen reserves and expelling carbon dioxide. Once submerged, it commits fully. Heart rate shifts almost immediately. What might beat steadily at the surface slows dramatically in the depths, a phenomenon known as bradycardia. By reducing cardiac output, the whale conserves oxygen and directs blood flow preferentially to vital organs, including the brain and heart, while peripheral tissues tolerate reduced supply. Metabolism slows, movement becomes economical. The whale does not thrash. It glides, propelled by powerful yet measured strokes of its flukes. Each descent is a mission measured in tens of minutes, sometimes approaching an hour, during which every second of oxygen must be budgeted. There is no margin for wasted energy in this black environment. In this near-total darkness, the acoustic landscape becomes the whale's primary frame of reference. Initially, the clicks are spaced widely apart, exploratory pulses scanning large volumes. As echoes return, faint outlines begin to assemble in the whale's internal map. The slope of a thermal boundary layer, a drifting gelatinous body, the distant presence of something more substantial. When a potential prey item is detected, the clicking rate changes. Pulses become more frequent, transitioning into what researchers describe as a creak phase. Rapid-fire bursts that refine the acoustic image as the whale closes in. The narrowing of the beam increases precision, focusing acoustic energy on a single target. In a world where prey can detect pressure waves and faint disturbances, stealth must be balanced against sensory resolution. The sperm whale's clicks are powerful, but their directionality reduces unnecessary broadcast, concentrating information rather than scattering it. Deep-sea squid, particularly large species that inhabit mid-water layers, are among the whale's primary targets. These animals are not passive. They possess their own suite of adaptations to darkness. Large eyes tuned to detect bioluminescent flashes, chromatophores that can alter skin patterns, and in some species, muscular mantles capable of rapid jet propulsion. When a squid senses the approach of a predator, it may accelerate abruptly, releasing ink not for visual concealment in darkness, but as a chemical and tactile decoy. The whale's echolocation, however, is less easily deceived by clouds of ink than by sudden changes in position. The battle in blackwater is therefore dynamic, a contest between acoustic tracking and erratic escape maneuvers. The whale's body is built to withstand this pursuit. Its thick skin and underlying blubber provide insulation in waters where temperatures hover near freezing. Thermal regulation in such depths is not trivial. Prolonged exposure to cold can impair muscle performance and metabolic processes. The blubber layer acts as both insulation and energy reserve, ensuring that during extended dives, core temperature remains stable despite reduced blood flow to peripheral tissues. Meanwhile, the tailstock, reinforced with connective tissue and muscle, delivers controlled bursts of propulsion when needed. The whale does not waste oxygen on constant acceleration. It conserves, waits, and then commits when acoustic certainty justifies the expenditure. At the moment of interception, the final approach is often rapid. The creaking clicks intensify, echo intervals shorten, and the whale's jaws open. Unlike toothed dolphins that often seize small fish, the sperm whale is adapted to engulf large prey. Its lower jaw is narrow but lined with conical teeth that interlock with sockets in the upper jaw. The suction generated as it opens its mouth, combined with forward momentum, draws the squid inward. In some encounters, resistance is fierce. Squid tentacles lash outward. Suction cups lined with chitinous rings clamp onto the whale's skin. These rings can cut, leaving circular scars that persist long after the encounter ends. When the whale eventually returns to the surface, those scars tell a story written in tissue. Circular marks, sometimes large and patterned, dot the head and flanks. They are not superficial abrasions, but evidence of repeated engagements with powerful cephalopods. In darkness, no human eye has witnessed directly. The whale does not hunt once and retreat permanently. It descends again and again over years and decades, refining technique, surviving conflict, and accumulating the marks of its profession. Each scar is proof that deep hunting is not a one-sided execution, but a risk-laden confrontation in an environment that punishes error immediately. The abyss, then, is not merely deep water. It is a sound, structured battlefield where vision is irrelevant and physiology determines survival. The sperm whale's life is shaped by the physics of pressure, the chemistry of oxygen binding, and the geometry of acoustic reflection. Its dives are not reckless plunges into darkness, but calculated missions governed by internal reserves and external signals. In committing to a single target in a nearly empty volume of water, the whale demonstrates a strategy built on patience and precision rather than frenzy. It must search widely, commit carefully, and execute efficiently before oxygen limits demand ascent. As it surfaces, exhaling explosively into the open air, sunlight reclaims its body, and waves reflect off scarred skin. For a moment, it appears serene, floating in brightness. Yet beneath that calm surface is an acoustic warrior, adapted to a realm where sight fails and sound defines existence. The scars etched across its head are not merely remnants of struggle. They are evidence that even in the deepest blackwater, predation is contested. Survival is earned repeatedly, and evolution has engineered a mammal capable of turning darkness into a navigable, measurable, and conquerable world. When daylight fades into the diluted blue of deeper water, vision does not disappear. It transforms. Edges soften, contrasts sharpen, and the ocean becomes a stage where even the faintest shift in brightness can dominate perception. In this diluted light, information is scarce but amplified. A flicker matters. A pulse of pale against dark becomes an event. Within this realm of visual scarcity, the cuttlefish does not merely blend into its surroundings, it manipulates them. It does not hide in the traditional sense. It broadcasts illusions calibrated to the limits of another animal's nervous system. The seafloor beneath is a mosaic of rock fragments, algae, and suspended sediment drifting in slow spirals. Visibility is moderate, but clarity is deceptive. Prey species, small crabs, shrimp, and juvenile fish, rely heavily on detecting motion and contrast rather than fine detail. Their survival depends on recognizing the approach of predators before the final lunge. The cuttlefish understands this limitation intimately because its body is a living screen capable of rewriting contrast in real time. Across its skin lie chromatophores, pigment sacs surrounded by radial muscles that expand and contract under direct neural control. Beneath them sit iridophores and leucophores, layers that reflect and scatter light. The coordination between these elements is not random. It is controlled with extraordinary precision by a complex nervous system that dedicates significant neural bandwidth to visual processing and skin modulation. When the cuttlefish hovers above the seabed, its body may display a muted, mottled pattern that mirrors the substrate. Yet this is only the baseline state. The true weapon is motion within pattern. Rather than remaining static, the cuttlefish can send waves of darkening and lightening across its skin in rhythmic pulses. Bands of contrast ripple from head to mantle, creating the illusion of movement independent of actual body displacement. To prey animals attuned to detecting predators by tracking directional motion, these waves can scramble timing. The prey sees movement, but not forward movement. The predator appears to flicker in place, dislocating expectation. In dim water, even slight variations in brightness are exaggerated by the eye's adaptation to low light. Photoreceptors in prey species shift toward higher sensitivity, sacrificing detail for brightness detection. Under these conditions, a narrow band of pale expanding across a darker background can dominate visual attention. The cuttlefish exploits this physiological bias. Pattern flashing becomes a tool of distraction, drawing focus away from the subtle forward glide that closes distance. The approach itself is deliberate and measured. The cuttlefish does not surge forward immediately. It drifts, buoyed by subtle fin undulations along the mantle's edge. These lateral fins generate a hovering motion that appears almost detached from propulsion. The body remains stable while the skin flickers. A small shrimp perched near a rock registers shifting contrast. It does not detect a direct line of attack. Its neural circuits interpret the rippling pattern as ambiguous background movement, not imminent threat. As the cuttlefish narrows the gap, it reduces large-scale body motion further. The illusion intensifies. Some species produce alternating bars that travel across the body at variable speeds, creating a phenomenon that researchers describe as passing cloud display. In territorial contexts, this display signals aggression to rivals. In hunting contexts, the same mechanism confuses prey, saturating the visual field with dynamic contrast. The prey's reaction timing falters because its escape reflex depends on detecting consistent forward motion or expanding silhouette. In deeper water, where light intensity drops further, the margin for contrast shrinks. A slight increase in reflectivity becomes conspicuous. Cuttlefish possess the ability to adjust not only hue, but also polarization of reflected light. Many marine organisms can detect polarized light, perceiving patterns invisible to humans. By altering the polarization characteristics of its skin, The cuttlefish may influence how prey perceives brightness gradients, adding another layer of manipulation. This is not camouflage in the static sense. It is visual interference. The strike, when it comes, is abrupt and precise. Two specialized tentacles, longer than the remaining arms and stored in pockets beneath the head, shoot forward in a fraction of a second. They extend beyond the body length, propelled by muscular hydrostatic pressure, and their clubbed tips adhere to the prey with suction. The timing of this extension is critical. If launched too early, the prey might react. If delayed, the distance becomes too great. The tentacles retract instantly, drawing the captured organism toward the beak. The entire event is nearly silent, a brief acceleration following prolonged deception. This ambush sequence reflects a balance between patience and explosive mechanics. The cuttlefish cannot sustain high-speed pursuit. Its mantle-driven jet propulsion is effective, but energetically costly and disruptive. Instead, it invests in neural computation and pattern control. In environments where light is scarce, altering perception may be more efficient than increasing velocity. Intelligence here operates at the interface of sensory biology and physics. The ecological implications extend beyond individual hunts. Cuttlefish often inhabit transitional zones where shallow reef meets deeper slope, areas influenced by currents and fluctuating turbidity. These environments demand adaptability. During daylight, pattern displays may emphasize blending with substrate textures. At dusk, when silhouettes blur and contrast sharpens, flashing patterns become more advantageous. The same neural circuitry supports both concealment and misdirection, toggling strategies according to ambient light conditions. Thermoregulation in cuttlefish aligns with their ectothermic nature. Water temperature influences metabolic rate and neural processing speed. In cooler, deeper layers, muscle contraction and tentacle extension may slow slightly. However, the reliance on deception rather than endurance swimming mitigates this constraint. By reducing the need for prolonged chases, the cuttlefish conserves energy in cold water while still maintaining effective predation. Predators of cuttlefish include larger fish, sharks, and marine mammals. When threatened, the cuttlefish employs a different suite of visual tactics. Rapid flashes, high contrast displays, and sudden shifts in brightness can startle attackers momentarily. Ink release provides additional obscuration, but even the ink may be deployed strategically, forming a pseudomorph that mimics the cuttlefish's shape. The predator, confronted with a decoy silhouette and residual pattern after images, may miscalculate direction. Once again, perception becomes the battlefield. In blackwater conditions, where light dwindles toward near darkness, the value of any visual cue increases. A faint ripple of brightness across skin can serve as both lure and shield. Prey species accustomed to scanning for larger, consistent shapes may overlook a flickering field of contrast that does not conform to typical predator outlines. The cuttlefish leverages this mismatch between expectation and reality. There is an understated irony in the cuttlefish's design. It lacks the imposing jaws of sharks or the massive bulk of rays. Its power lies in subtlety and timing. The living screen of its skin is not decorative display, but an interface between its nervous system and the sensory limitations of others. In water where vision becomes uncertain, it writes confusion directly onto its body. As the cuttlefish drifts deeper into the blue-black gradient, its patterns adjust. The brightness pulses diminish, replaced by softer modulation suited to reduced light. The seabed below fades into obscurity, yet the cuttlefish remains distinct in its quiet control. A small fish wanders into the ambiguous space between shadow and glow. The cuttlefish holds position, skin shimmering with controlled irregularity. The fish hesitates, its neural circuits passing flicker without direction. The tentacles extend in a single decisive motion. The illusion collapses into capture. In this layered ocean, where light governs behavior as much as hunger, the cuttlefish demonstrates that warfare need not be violent to be effective. Visual manipulation, tuned precisely to environmental context, can replace brute force. The living screen moves through blackwater not as a passive reflector, but as an active author of perception. Here, in the diluted glow between reef and abyss, The cuttlefish turns contrast into weaponry and timing into fate, proving that in dim light, control of what others see can determine who survives. The seabed at the edge of the continental slope is not a landscape in the familiar sense. It is a gradual descent into pressure and darkness, where the sediment absorbs sound and light alike, and where life arranges itself around scarcity rather than abundance. Fine particles drift down from distant surface waters in a continuous, invisible snowfall of organic debris. Most of what reaches this depth is already stripped of its richest nutrients by organisms above, leaving behind a thin rain of leftovers. In this economy of remnants, every calorie carries disproportionate value. Movement here is deliberate. Energy is currency. And on this muted plain, partially buried in silt and shadow, lies a creature that has converted patience into predatory precision. The monkfish does not resemble a hunter in the conventional sense. Its body is broad and flattened, colored in mottled browns and grays that mirror the sediment it rests upon. The skin is textured, uneven, blending seamlessly with the substrate. The head appears oversized, dominated by a cavernous mouth that seems disproportionate to the rest of the body. From the forehead projects a slender, flexible spine, the first dorsal fin ray, modified into a structure known as the elysium. At its tip hangs a fleshy appendage, the esker, shaped and pigmented in ways that suggest vulnerability rather than danger. In a world where edible matter is rare and scattered, this small imitation of prey becomes a signal impossible to ignore. The abyss is not empty, but it is unpredictable. Small fish and crustaceans patrol the seafloor in search of organic fragments or living prey. Visibility is limited. Even the most sensitive eyes must contend with dim, diffuse light, or complete darkness, broken only by bioluminescent flashes. In such conditions, animals rely heavily on detecting motion rather than detailed shape. The monkfish exploits this bias. The elysium can be moved independently of the body, twitched and waved with subtle control. The esker may emit faint bioluminescent glow in some species, further enhancing its illusion as a small organism adrift in the water column just above the sediment. Against the static background of the seabed, this small, moving point becomes conspicuous. For a small fish navigating this environment, the decision to investigate is driven by necessity. Hunger sharpens reflexes and narrows options. When food is scarce, hesitation can mean starvation. The moving lure mimics the erratic pattern of a struggling invertebrate or drifting planktonic organism. In low visibility, the distinction between real prey and imitation collapses into a simple rule: strike at small moving targets before competitors do. Evolution has wired many fish with this reflex. The monkfish depends on it. The true mechanism of predation, however, is not in the lure, but in the mouth beneath it. The monkfish's jaws are constructed for rapid expansion rather than sustained biting. The bones of the skull are loosely articulated, capable of spreading outward to increase volume dramatically in a fraction of a second. When prey moves within range, the monkfish does not lunge forward in pursuit. It opens. The mouth drops downward and outward, and at the same instant, the floor of the buccal cavity depresses sharply. This action creates a sudden negative pressure relative to the surrounding water. Water, and anything suspended within it, rushes inward to equalize the pressure difference. Suction feeding is a common strategy among many fish, but in the monkfish, it is refined to an extreme. The speed of mouth opening and cavity expansion generates a flow so rapid that prey has virtually no opportunity to react. There is no prolonged struggle, no visible chase. From an external perspective, it appears as though a door has swung open and the water itself has delivered the victim inside. Once engulfed, backward-pointing teeth prevent escape, and the jaws close with finality. The entire event unfolds in less time than a startled fish can process the threat. This strategy reflects a fundamental constraint of the deep environment. Active pursuit requires energy, and energy at these depths is not replenished quickly. Muscles consume oxygen and stored fuel. In cold, high-pressure conditions, metabolic processes are slowed, but they are not free. The monkfish has adopted a lifestyle that minimizes expenditure. It spends extended periods motionless, partially buried, allowing sediment to settle across its body. Its coloration and texture reduce detection by both prey and potential predators. In remaining still, it avoids attracting attention and conserves energy reserves that might otherwise be wasted in fruitless chases. Patience in this context is not passive resignation, but calculated strategy. The monkfish has traded speed for inevitability. By transforming its own body into terrain, it removes itself from the dynamic field of moving organisms and instead becomes a fixed point in the environment. Prey scanning the seafloor for irregularities are more likely to focus on isolated movement, such as the twitch of the esker, rather than the broad, unmoving shape beneath. This selective attention is a vulnerability. In a low-light world, the brain prioritizes contrast and motion. The monkfish supplies both in controlled, minimal doses. The physics of suction feeding also reveal deeper evolutionary compromises. To generate such rapid expansion, the musculature surrounding the skull must be capable of powerful contraction. However, these muscles are used sparingly. The monkfish cannot sustain repeated rapid strikes without recovery. Its survival depends on the efficiency of each attempt. A missed strike represents not only lost opportunity, but also wasted energy. As a result, the timing of the attack is critical. The monkfish allows prey to approach within a precise distance before triggering the mechanism. Too early, and the pressure gradient weakens before the prey is within capture range. Too late, and the prey may detect the outline of the predator. Prey species are not defenseless participants in this exchange. Many possess lateral line systems sensitive to minute changes in water movement. The rapid inrush of water preceding a suction strike can, in theory, be detected, yet detection does not guarantee escape. The time between the onset of water acceleration and full engulfment is so brief that even a triggered reflex may not translate into sufficient movement. Additionally, hunger can override caution. In nutrient-poor environments, prey may be forced to accept higher risks, approaching moving objects more readily than they would in food-rich habitats. This ecological pressure benefits the monkfish. Scarcity weakens the vigilance of others. There is a quiet irony in the monkfish's form. Its appearance suggests clumsiness, even lethargy, yet its feeding apparatus operates with surgical precision. The exaggerated mouth, which might seem excessive, is precisely proportioned to maximize the volume of water, and therefore prey, captured in a single strike. The expandable stomach allows ingestion of prey nearly as large as the predator itself, an adaptation to unpredictability in food availability. When a substantial meal is captured, the monkfish can endure extended periods without feeding again, relying on stored energy, while the digestive process extracts maximum value. In deeper zones where absolute darkness prevails, the lure may incorporate bioluminescent bacteria housed within specialized tissues. These symbiotic microorganisms produce light through chemical reactions involving luciferin and luciferase, creating a glow that the monkfish can modulate by adjusting exposure or blood flow. This relationship exemplifies the deep sea's reliance on biological light as currency of interaction. The monkfish does not generate light independently, but cultivates it, providing habitat for bacteria that in turn enhance its predatory reach. The faint glow becomes a beacon in a world starved of illumination, a promise of nourishment that conceals annihilation. The seabed around the monkfish remains largely undisturbed. Small crustaceans scuttle, fish patrol cautiously, and particles continue their descent from above. Nothing in the immediate environment signals imminent violence. The predator's stillness is so complete that it blends into geological time. Yet beneath that stillness lies readiness, a mechanism primed for instantaneous transformation from inert landscape to consuming force. The abyss rewards such strategies. In a realm where energy budgets are tight and encounters are rare, success belongs to those who can convert minimal movement into maximal gain. The monkfish's existence underscores a broader principle of deep-sea ecology. Power does not always manifest as speed or size. Sometimes it resides in restraint. In refusing to chase, in refusing to waste, the monkfish aligns itself with the constraints of its environment. Its trapdoor mouth is not merely a dramatic feature, but a solution to the problem of scarcity. By allowing physics to perform the final act, by letting water deliver prey inward, it reduces the need for muscular exertion and prolonged struggle. As the camera lingers on the seabed, the Elysium sways gently, almost imperceptibly. A small fish, driven by hunger and guided by reflex, edges closer. In the darkness, the distinction between opportunity and threat dissolves into a single moving point of light. The monkfish does not move until it must. Then the door opens, the water surges, and the illusion collapses into silence. The sediment settles once more, and the predator returns to stillness, an indistinguishable part of the abyssal floor, waiting for the next mistake to drift within reach. Far below the warm turbulence of coral reefs and sunlit lagoons, where color dissolves into monochrome and the concept of beauty loses relevance, a different kind of angelfish drifts through the water column. There are no branching corals here, no symphonies of reef fish weaving through anemones. The environment is a vertical desert of cold water and crushing pressure, where the faintest glimmer of light may come not from the sun, but from living tissue. In this realm, form follows necessity with uncompromising honesty. What might appear grotesque to a surface observer is, in truth, a design honed by scarcity and physics. The deep-sea angelfish is not adorned for admiration, it is constructed for efficiency. The first impression is often the mouth. It appears disproportionate, stretching wide across the head, framed by elongated jaws lined with needle-like teeth. These teeth are not decorative exaggerations, they are mechanical solutions. In the abyss, prey is not abundant, and encounters are infrequent. A predator cannot afford to be selective. When an opportunity presents itself, the ability to secure and retain that prey is paramount. The jaws are loosely articulated, capable of expanding beyond what the skull's resting shape might suggest. Ligaments allow the bones to separate and flare outward, increasing the gape dramatically. This structural flexibility means that prey nearly equal in size to the predator can be swallowed whole. The stomach, too, is expandable, its walls capable of stretching to accommodate meals that may sustain the fish for extended periods. In the deep ocean, energy arrives unpredictably. Organic matter drifts downward from surface waters in a slow, uneven rain, and larger prey migrate vertically or patrol sparse feeding grounds. A predator that relies on small, frequent meals would expend more energy searching than it would gain from consumption. The angelfish's oversized mouth is therefore a storage strategy as much as a capture device. When prey appears, it must be engulfed decisively, even if digestion will require time and metabolic adjustment. The expandable stomach allows the fish to convert rare abundance into prolonged survival, storing nutrients in an environment where the next meal may be separated by days or more. The body surrounding this formidable head is streamlined, but not built for sustained pursuit. Fins are modest, suited to controlled hovering and short bursts rather than marathon chases. In the abyss, chasing prey over long distances is inefficient. The water is cold, slowing muscle contraction and reducing metabolic rates. Oxygen availability, though sufficient, must be balanced against the energy cost of active hunting. Instead, many deep-sea predators adopt strategies centered on ambush or opportunistic interception. The angelfish often positions itself within mid-water layers where migrating organisms pass. It does not race through the darkness. It waits within it. Waiting in darkness requires sensory systems adapted to minimal light. The eyes of deep-sea angelfish are proportionally large, their retinas tuned to detect faint contrasts rather than vibrant colors. In these depths, color information is largely irrelevant. Red wavelengths vanish quickly with depth, leaving a blue-dominated spectrum that fades to black. The retina contains photoreceptors optimized for sensitivity, enabling detection of bioluminescent flashes that punctuate the darkness. Bioluminescence is not rare here. It is a language spoken by countless organisms. Some emit light as warning, others as lure, and many as camouflage. Counter-illumination is one of the most remarkable adaptations in this environment. Certain fish possess light-producing organs along their bellies that emit a glow matching the faint downwelling light from above. When viewed from below, their silhouette dissolves against the background, rendering them nearly invisible to predators scanning upward. While not all angelfish employ this exact mechanism, The broader principle underscores the importance of light manipulation in the abyss. Light is not merely illumination, it is deception, communication, and concealment combined. In some deep-sea species, luminous tissues near the mouth or along the body may attract curious prey, drawing them within range of a sudden strike. The angelfish's face, then, becomes more than a sensory platform. It is a weaponized interface. The elongated teeth are often angled inward, forming a cage that prevents slippery prey from escaping once captured. Many deep-sea organisms possess smooth, gelatinous bodies designed to reduce drag and conserve energy. Such prey can be difficult to grip. The teeth compensate for this slipperiness, ensuring that once the jaws close, retreat is nearly impossible. The mechanics of the bite are swift. Like other suction-feeding fish, the angelfish can expand its buccal cavity rapidly, generating a pressure differential that draws water and prey inward. The combination of suction and interlocking teeth transforms a fleeting encounter into a secure capture. In the abyss, the face frequently signals feeding strategy. Large mouths and protruding teeth may appear monstrous, but they reflect ecological pressures rather than aesthetic deviation. A predator that fails to secure prey on the first attempt may not encounter another opportunity soon. There is little margin for error. As a result, morphological exaggeration becomes adaptive. Jaws enlarge, teeth lengthen, stomachs stretch. Efficiency overrides elegance. What might seem excessive in a reef environment teeming with small fish is entirely rational in a sparsely populated depth. Thermoregulation in this realm presents additional constraints. Water temperatures remain near freezing, and the metabolic processes of ectothermic fish slow accordingly. Reduced metabolic rates can be advantageous, lowering energy demands during long intervals between meals. However, muscle performance declines in cold conditions, limiting sustained activity. The angelfish's reliance on short, decisive strikes aligns with this thermal reality. Rather than engaging in prolonged chases that would quickly deplete energy reserves, it capitalizes on proximity and timing. Cold water thus shapes behavior as much as morphology. The angelfish's presence within vertical migratory pathways further illustrates its integration into deep-sea dynamics. Many smaller organisms undertake diel vertical migrations, ascending towards surface waters at night to feed and descending during daylight to avoid visually oriented predators. These movements create temporary corridors of prey density within otherwise sparse waters. Predators positioned strategically along these routes can intercept migrating individuals with minimal expenditure. The angelfish's body plan, optimized for sudden engulfment rather than endurance swimming, aligns with such opportunistic feeding. Bioluminescence also influences predator-prey interactions in subtler ways. When disturbed, some prey species emit brief flashes intended to startle or distract predators. In darkness, a sudden burst of light can disrupt visual focus momentarily. Yet predators adapt. Eyes sensitive to low light can recover quickly, and the angelfish's strike relies less on prolonged visual tracking than on immediate proximity. The interplay between luminous signals and rapid capture reflects an ongoing evolutionary negotiation. As prey refine their light-based defenses, predators refine their timing and jaw mechanics. Even the angelfish's coloration, often muted and dark, serves a purpose. Pigments that absorb residual light reduce reflectivity, minimizing the chance of detection. In an environment where any contrast may reveal presence, blending into the surrounding blackness is critical. Some deep-sea fish possess skin so dark that it absorbs nearly all incident light, rendering them nearly invisible when illuminated. While angelfish vary in degree of pigmentation, the trend toward darkness reflects a broader principle. Concealment is achieved not through elaborate pattern, but through the absence of reflection. The deep sea fosters designs that may appear unsettling, yet each trait corresponds to measurable pressures. Oversized mouths reflect irregular feeding opportunities. Expandable stomachs accommodate rare windfalls. Needle-like teeth secure gelatinous prey. Large eyes interpret faint signals. Reduced musculature favors energy conservation over speed. Even the seemingly exaggerated head-to-body ratio becomes logical when viewed as an investment in capture efficiency rather than locomotion. As the camera drifts alongside an angelfish suspended in the black water, its silhouette is defined by the faintest ambient glow. The mouth remains slightly agape, teeth poised. There is no overt aggression in its posture, only readiness. A small fish navigating through the darkness registers a faint movement ahead. In this environment, hunger shapes decisions quickly. The distance closes. In an instant, the jaws flare, the cavity expands, and the water rushes inward. The event is brief, silent, and final. There is no extended pursuit, no dramatic thrashing. The efficiency is almost clinical. The angelfish's design challenges surface expectations of beauty. But in the abyss, beauty is measured in survival. Each structural exaggeration represents a response to environmental constraint. The face, which might appear distorted to human perception, is precisely proportioned to the demands of unpredictable meals and limited energy budgets. In a world where light is rare and encounters are fleeting, the mouth becomes destiny. Through this lens, the deep-sea angelfish is not a horror, but a testament to evolution's pragmatic clarity, a creature shaped by darkness into a form where efficiency overrides ornament and survival is written directly onto the architecture of the skull. At the surface, beneath a sky that fractures into shifting patterns across the waves, the whale shark moves with unhurried precision. Its back breaks the water like a slow, living reef, patterned in pale constellations against deep grey-blue skin. The mouth, wide and squared at the front of the head, remains partially open as it glides forward. Sunlight penetrates here, illuminating plankton suspended in shimmering columns, each particle reflecting light as though the ocean were filled with drifting dust motes. To an observer at the surface, the whale shark appears almost improbable in its restraint. A body the length of a city bus moves without violence, drawing in seawater and expelling it through gill slits along its flanks. There is no predatory chase, no explosive strike. Yet this animal, gentle in reputation, is tied intimately to one of the most dynamic processes in the open ocean, the daily vertical migration of life itself. Each evening, as the sun lowers and surface waters cool, vast communities of zooplankton and small fish ascend from deeper layers toward the light. This movement, known as diel vertical migration, represents one of the largest synchronized animal movements on Earth. Organisms that spend daylight hours in darker, deeper water to avoid visual predators rise under cover of night to feed near the surface. By dawn, they descend again. The vertical scale of this migration can span hundreds of meters, and its timing is finely tuned to light intensity rather than to the clock. For a filter feeder capable of consuming immense quantities of microscopic prey, this migration is not a minor detail. It is a predictable buffet that shifts location every day. The whale shark's feeding apparatus reflects this dynamic prey field. Inside the cavernous mouth are rows of tiny, backward-facing teeth, but these are not the primary tools of feeding. Instead, specialized filtering pads composed of cartilaginous structures trap plankton and small fish as water flows across the gills. The shark swims forward with its mouth open, allowing water to enter, then forces it out through the gill slits, where prey is retained. This method requires dense concentrations of food to be efficient. Scattered plankton would not justify the energy expenditure of constant filtration. The vertical migration solves this problem by concentrating biomass in moving layers. Tracking these layers demands more than passive drifting. The whale shark possesses a refined sensory system capable of detecting changes in water temperature, salinity, and perhaps subtle chemical cues associated with plankton blooms. As migrating prey ascend, they often form dense scattering layers, detectable even by sonar instruments deployed by humans. The whale shark appears to respond to these density gradients, adjusting its depth accordingly. It is not simply feeding at the surface because it is convenient. It is following a vertically shifting resource, aligning its movements with the rhythm of the ecosystem. Yet the story does not end at the surface. Despite its association with sunlit waters, the whale shark is known to undertake deep dives into colder, darker layers of the ocean. Satellite tagging, has revealed descents that extend far below typical surface feeding zones. These dives introduce a striking contrast: a massive plankton-feeding fish descending into near darkness where temperatures drop and pressure increases substantially. The reasons for these journeys are multifaceted and continue to be studied, but several ecological threads converge. One compelling factor is the extension of the vertical migration itself. While many prey ascend toward the surface at night, others remain at intermediate depths during the day, forming concentrated layers beyond the reach of surface light. A whale shark capable of diving to these depths can exploit feeding opportunities unavailable to surface-bound predators. Its size grants it thermal inertia, meaning its body temperature changes more slowly than that of smaller fish. Although it is ectothermic, relying on environmental temperatures to regulate internal conditions, the sheer mass of its body buffers rapid fluctuations. This thermal inertia allows it to traverse cooler layers without immediate metabolic compromise. Deep dives may also serve navigational functions. The ocean's interior is structured by gradients in temperature and salinity that create density layers. These layers influence currents and can carry chemical signatures of distant regions. By moving vertically, the whale shark may sample different strata, detecting cues that assist in long-distance orientation. The species is known for extensive migrations across ocean basins, and understanding the interplay between vertical and horizontal movement is essential. The ocean is not a flat plane, but a layered environment, and a three-dimensional traveler gains access to more information. Temperature regulation may provide another incentive for deep excursions. In warm tropical waters where whale sharks are frequently observed feeding at the surface, prolonged exposure to high temperatures can increase metabolic rates. By descending periodically into cooler water, the shark may reduce its metabolic demand temporarily, conserving energy. This behavior mirrors strategies seen in other large marine animals that shuttle between thermal layers to balance feeding efficiency with physiological stability. The contrast between warm surface water and cooler depths creates a natural gradient the shark can exploit. There is also the possibility of parasite management. Many large marine animals host external parasites that attach to skin or gill tissues. Sudden changes in temperature and pressure during deep dives could dislodge or impair some parasites, although definitive evidence for this function in whale sharks remains under investigation. Even if not a primary driver, such secondary benefits illustrate how behaviors may serve multiple ecological roles simultaneously. Descending into darkness, the whale shark's silhouette transforms. Sunlight fades, and the pattern of pale spots on its back becomes indistinct. In dim light, its immense size becomes more abstract, a moving mass rather than a clearly defined shape. Despite its scale, it remains silent, propelled by slow, powerful sweeps of its tail. There is a quiet tension in witnessing such a large organism slip into black water. It is not a predator of large prey, yet its mass and momentum carry undeniable presence. The fear factor arises not from aggression, but from magnitude. In an environment where many deep-sea predators are compact and armed with exaggerated features, the whale shark represents a different kind of power. Sheer volume navigating invisibly. At depth, light-sensitive organisms may detect its approach as a shifting shadow. Plankton layers disturbed by its passage ripple and reform. The shark opens its mouth and water flows inward, filtered methodically. Unlike pursuit predators that rely on bursts of speed, the whale shark's feeding depends on encountering dense patches. Its slow cruising is energy efficient relative to its size, and its metabolism, though substantial in absolute terms, is moderated by its ectothermic physiology. The balance between intake and expenditure is delicate. Without sufficient prey density, the energetic cost of maintaining such a large body would outweigh returns. The vertical migration buffet is not uniform across all oceans. Regional productivity, influenced by upwelling currents and nutrient input, determines where dense prey layers form. Whale sharks are often observed near coastal regions, where nutrient-rich water supports plankton blooms. Yet their capacity for deep diving suggests a flexibility that extends beyond coastal shallows. They can traverse open ocean expanses, diving through layers in search of scattered resources, then return to surface zones when conditions align. The scale of these movements defies intuitive perception. To imagine an animal of such magnitude sliding quietly into deep water challenges assumptions about vulnerability and dominance. The whale shark is not armored with aggression, yet it navigates realms shared by apex predators. Its defense lies in size and indifference rather than in teeth or speed. Few predators can threaten a mature individual, though juveniles may face greater risk. This relative safety allows the species to adopt a feeding strategy centered on abundance rather than confrontation. As dawn approaches and migrating prey begin their descent, the whale shark may follow briefly before reversing course. The cycle continues day after day, aligning its path with the ocean's daily pulse. Its body becomes a living bridge between layers, connecting surface productivity with deeper strata. In doing so, it participates in nutrient redistribution, excreting waste that re-enters the food web at varying depths. Even a filter feeder of plankton plays a role in shaping ecosystem dynamics. From the surface once more, the animal's spotted back catches the light. The immense mouth remains open, unthreatening yet purposeful. The gentle giant moniker reflects its feeding behavior rather than its ecological impact. It is a massive filter in a system defined by movement, tracking a buffet that rises and falls with the sun. Its deep dives reveal a complexity that transcends surface appearances. This is not a creature confined to warm, bright water. It is a vertical navigator, capable of traversing thermal and light gradients with quiet efficiency. In the vast, layered architecture of the ocean, the whale shark embodies a paradox. Immense, yet delicate in feeding, surface-bound in reputation, yet comfortable in darkness. Its presence in deep water does not signal predatory menace, but adaptive reach. It follows food, samples temperature, and moves through 3 dimensions with steady deliberation. The fear it evokes arises not from danger, but from scale and silence, from witnessing something so large vanish into black water without disturbance. In that descent lies a reminder that even the gentlest giants are shaped by the full depth of their environment, guided by rhythms that extend far beyond what the surface reveals. The abyss does not begin at the ocean floor. It begins each evening at the horizon. As the sun lowers and light stretches across the water in elongated bands, the sea reorganizes itself into gradients of contrast. The surface becomes a mirror of blinding glare, fractured by waves and refracted into chaotic brightness. Beneath that glare, just a few body lengths below, visibility shifts dramatically. Shapes flatten, colors dull. The ocean turns into a layered field of silhouettes and brightness gradients. This is the hour the great white shark understands intimately, because dusk is not simply a time of day. It is a structural advantage. From the perspective of a seal resting at the surface, the world below is murky and uncertain. Sunlight scatters downward, diffused by particulate matter and surface turbulence. The seal's eyes, adapted to both air and water, scan for obvious threats. Yet in this moment, the greatest threat is not lateral movement or surface disturbance. It is the absence of detail beneath the glare. The seal sees brightness above and darkness below. It does not see depth as a predator sees it. The great white positions itself in that darkness, not at the bottom, but suspended in the transitional layer where light fades into blue-black. In this zone, the shark's pale underbelly blends with the faint illumination from above, while its darker dorsal surface merges with deeper water below. Countershading, an evolutionary adaptation shared by many marine predators, is amplified by the optical confusion of dusk. The shark does not rush upward immediately. Its hunt begins long before the explosive strike. The ocean is filled with information invisible to surface observers. The lateral line system running along the shark's flanks consists of fluid-filled canals lined with sensory hair cells that detect minute vibrations and pressure changes. Every tail flick of a fish, every flipper stroke of a seal produces low-frequency disturbances that propagate through water. These signals travel efficiently, and in the relative quiet of twilight, they become clearer. The shark reads this vibration field as a 3-dimensional map of movement. Smell also plays a role long before sight. The shark's nostrils, positioned beneath the snout, sample water continuously. Chemical cues disperse through currents, revealing traces of blood, bodily fluids, or stress metabolites. While popular narratives exaggerate the distances at which sharks detect blood, their olfactory system is undeniably sensitive. At dusk, when visual cues are compromised by glare, chemical gradients become an early warning system of opportunity. The shark does not rely on a single sense. It layers information, constructing a probabilistic assessment of prey location. As the light fades further, prey animals often alter behavior. Seals may increase surface activity before nightfall, feeding or traveling between haul-out sites. Fish schools shift depth. The interplay of movement and glare creates a series of blind zones. From below, looking upward, the shark perceives the silhouette of a seal against the bright surface. From above, looking downward, the seal struggles to distinguish a rising shadow against the glare. This asymmetry defines the ambush. The great white's body is engineered for a singular mechanical act. It is not built for sustained high-speed pursuit like some open-ocean predators. Instead, its musculature concentrates power in a short, explosive burst. The caudal fin, crescent-shaped and rigid, can generate tremendous thrust when driven by strong axial muscles along the body. Prior to the strike, the shark reduces motion, conserving energy and minimizing detectable turbulence. It aligns itself beneath the target, maintaining depth just beyond the prey's comfortable visual range. Timing is critical. If the shark ascends too early, the seal may detect a shifting silhouette and evade. If it ascends too late, the opportunity passes. The shark waits for the moment when the prey's escape reflex is least prepared, often when the seal is engaged in surface behavior such as feeding or reorienting. Then the ascent begins. The initial acceleration is controlled, maintaining minimal turbulence. As distance closes, the shark increases power, converting stored muscular energy into vertical momentum. Water resistance builds, but the shark's streamlined body reduces drag. In the final instant, the jaws open, exposing rows of serrated teeth designed not merely to puncture, but to slice. The strike itself is brief, often lasting less than a second from emergence to impact. In some cases, the shark breaches the surface entirely, its body arcing into the air with captured prey. The mechanics are simple: approach unseen, accelerate explosively, intercept before escape reflex completes. Escape timing in prey relies on detecting an approaching threat and initiating a rapid response. At dusk, the visual cue arrives too late. The prey's nervous system cannot process the shadow quickly enough to translate perception into motion. The shark exploits this neural delay. Not every strike results in immediate consumption. In certain contexts, particularly with larger prey, the shark may deliver a powerful initial bite and then withdraw, allowing the prey to weaken from blood loss before returning. This behavior reflects risk management. Large prey can inflict injury, and the shark's strategy balances aggression with caution. Even here, dusk offers advantage, as reduced visibility limits the prey's capacity to track the predator's repositioning. The twilight zone also influences thermoregulation and muscle performance. Unlike many fish, great white sharks exhibit regional endothermy. Through a countercurrent heat exchange system known as the rete mirabile, heat generated by muscle activity is retained within the body core rather than dissipated rapidly into surrounding water. This allows the shark's swimming muscles and internal organs to remain warmer than ambient seawater. In cooler twilight waters, this thermal advantage translates into more powerful contractions and faster reaction times compared to cold-blooded prey. The predator's internal temperature becomes a hidden asset in low-light ambush. As darkness deepens, the boundary between shallow hunting grounds and the deeper ocean blurs. The abyss begins at dusk, not because of depth, but because of perception. Light no longer defines clear outlines. It creates ambiguity. In this ambiguity, the shark thrives. Its eyes, equipped with a reflective layer behind the retina, known as the tapetum lucidum, enhance sensitivity in low light. This adaptation increases the probability of detecting silhouettes against fading brightness. Combined with lateral line input, and olfactory cues, the shark operates with layered redundancy. If one sense yields incomplete data, another compensates. The mechanical nature of the hunt becomes evident when viewed without dramatization. There is no extended chase across miles of open water. The shark does not expend energy in prolonged pursuit. It positions, calculates, and commits. The simplicity of the sequence belies its effectiveness. Evolution has shaped an organism that capitalizes on a predictable environmental transition. The daily shift from glare to shadow. Prey species adapt in response. Seals may vary entry angles into water, scanning for unusual patterns. Fish schools may tighten formation at dusk. Yet the physics of light cannot be fully neutralized. The upward glare remains blinding from certain angles, and any organism silhouetted against it risks becoming a target. The shark's rise from below leverages this optical constraint. Even after a successful strike, the shark's behavior remains measured. It does not thrash aimlessly. Powerful jaws and serrated teeth ensure that once contact is made, tissue yields quickly. The energy gained from a single large prey item may sustain the shark for days or longer, reducing the need for repeated risky engagements. This energy efficiency mirrors strategies observed in other apex predators inhabiting environments where food availability fluctuates. As night settles and the surface glare disappears entirely, the ambush dynamic shifts. In full darkness, the visual silhouette advantage diminishes. The shark may descend slightly, adjusting strategy as prey behavior changes. The twilight window closes, but it will reopen with the next sunset. The ocean's daily rotation ensures repetition of this opportunity. In the fading light, as a final glow lingers on the horizon, the shark drifts beneath the surface once more. Its presence is not announced by sound or splash. It is a shadow among gradients, a form that understands the geometry of light. The abyss has begun not in depth, but in contrast. And within that contrast, the great white executes its role with mechanical precision. The hunt is not chaotic. It is timed, layered, and efficient. In the moment when glare blinds and reflex falters, the predator ascends, and the outcome is decided before the prey understands what has risen from below. One predator is intimidating in its size and strength. A plan is something else entirely. In the open ocean, where depth replaces landscape and water erases tracks, strategy becomes a physical force. Beneath a steel-gray sky, a pod of orcas moves in quiet formation, dorsal fins cutting through the surface with geometric precision. They are not rushing. There is no visible urgency. Yet their spacing is deliberate, their orientation unified, their breathing synchronized in intervals that suggest calculation rather than coincidence. In these waters, intelligence is not abstract. It is embodied in movement, spacing, and restraint. The ocean around them appears vast and undifferentiated, but to the orcas, it is layered with information. Sound travels more efficiently through water than through air, and every pulse carries detail. Orcas produce a range of vocalizations, from high-frequency clicks used in echolocation to whistles and pulsed calls that serve communicative roles within the group. When foraging begins, the acoustic landscape shifts. Echolocation clicks map the surrounding volume, revealing fish schools as shimmering clusters of reflected sound. Each echo provides data on density, size distribution, and movement. The pod does not attack immediately. They circle, adjusting depth and spacing, sampling the shape of the prey from multiple angles. The prey, often schooling fish such as herring, rely on collective motion for defense. By forming dense aggregations, they reduce individual risk, confusing predators through rapid, synchronized turns. However, the orcas respond not with a frontal assault, but with choreography. A subset of individuals positions below the school, emitting bursts of bubbles that rise in curtains, creating a visual and tactile barrier. Others approach from the sides, tightening the school's formation. The goal is not to scatter, but to compress. As the fish pack closer together, their maneuverability declines. Oxygen levels within the dense mass may drop slightly, increasing stress. In this tightening sphere, individual fish become more predictable. Rotation becomes visible in the attack sequence. One orca surges upward, striking the edge of the ball with a forceful tail slap that stuns multiple fish simultaneously. It withdraws, allowing another individual to enter the breach. The attackers alternate, conserving energy and preventing fatigue. No single animal dominates the effort. Each contributes in sequence, maintaining pressure while minimizing individual expenditure. This rotational hunting reflects not only physical capability, but social structure. Trust and communication underlie the choreography. A mistimed entry could disrupt the formation and allow the prey to escape. Precision is maintained through constant acoustic feedback and subtle body cues. Sound itself becomes a tool of manipulation. During coordination, orcas may vocalize loudly, reinforcing cohesion within the pod. When stalking more sensitive prey, such as marine mammals, they can fall nearly silent, reducing echolocation clicks to avoid detection. Some fish species can detect certain frequency ranges, responding to predator clicks with evasive maneuvers. Orcas appear capable of modulating their acoustic output depending on context, balancing the need for information with the risk of alerting prey. In this adaptive use of sound, intelligence is audible. As the school fragments and stunned fish drift downward, individual orcas seize their share. The efficiency of the plan is evident not in spectacle but in outcome. Few fish escape the compressed zone. Energy gained exceeds energy spent. The pod regroups, their breathing steady, their formation re-established. The ocean surface smooths as if nothing occurred. Yet orca strategy extends beyond surface hunting. Some populations pursue prey that descends into deeper layers to evade attack. In these scenarios, the water darkens quickly and visibility diminishes. Here, teamwork grows even more critical. A solitary predator diving into low-light conditions may struggle to maintain contact with agile prey. A coordinated group can triangulate. By spreading vertically and horizontally, individuals maintain acoustic contact with both prey and one another. Echolocation clicks bounce between bodies and targets, creating a shared acoustic map. Through this collective sensing, the pod tracks movement that would elude a single hunter. Deep dives impose physiological challenges. Orcas, like other marine mammals, store oxygen in blood and muscle rather than relying solely on lung capacity. Prior to submerging, they inhale deeply, replenishing reserves. Once below, heart rate slow, conserving oxygen and prioritizing circulation to vital organs. Muscles rich in myoglobin hold oxygen for sustained activity. These adaptations allow dives lasting several minutes, sufficient to pursue prey into dim layers. However, speed at depth is costly. Water resistance increases with velocity, and prolonged high-speed chases deplete oxygen reserves rapidly. Cooperation mitigates this cost. By alternating positions and sharing pursuit, individuals avoid exhausting themselves in solitary effort. Low light conditions alter the sensory balance. Vision becomes secondary, while echolocation gains prominence. Orcas emit focused clicks, listening for echoes that reveal the contours of fish bodies or the silhouettes of diving seals. Prey descending into darkness may hope to lose visual contact, but sound ignores light boundaries. In these depths, the pod's acoustic network becomes a web, capturing signals from multiple angles. One individual's echo complements another's, reducing blind spots. Collective cognition emerges not only from brainpower, but from distributed perception. There are instances where orcas intentionally drive prey toward less favorable environments. Fish may be herded toward shallower waters where escape routes narrow. Marine mammals may be separated from groups and forced into open expanses. In polar regions, orcas have been observed coordinating to generate waves that wash seals from ice floes. Each tactic reflects anticipation of prey behavior. The predator does not merely react, it predicts and shapes outcomes. The cognitive load of such operations is significant. Individuals must understand their roles, adjust to shifting conditions, and maintain cohesion. Social bonds within pods are strong, often matrilineal, with knowledge transmitted across generations. Hunting techniques can be culturally specific, varying between populations. The abyssal tie-in reveals a subtle dimension of this intelligence. When prey descends beyond typical hunting depths, Some orcas follow, despite colder temperatures and increasing pressure. Thermal regulation in these dives depends on insulating blubber layers and countercurrent heat exchange systems in the extremities, which minimize heat loss. While not as deep diving as sperm whales, orcas demonstrate flexibility and depth usage that expands their ecological reach. In pursuing prey into darker zones, they rely less on individual speed and more on group coordination to compensate for reduced visibility. A solitary predator in darkness is limited by the angle and reach of its senses. A coordinated group can surround, compress, and redirect. If one individual loses acoustic contact momentarily, another may retain it, preventing prey from slipping through a sensory gap. The value of a plan becomes clear in such scenarios. One predator is formidable. Multiple predators operating under shared intent are exponentially more so. The fear factor lies not in teeth alone, but in anticipation. Prey confronted by a coordinated pod faces not a single vector of attack, but a dynamic system adjusting in real time. Even rest periods reflect social intelligence. Pods often travel in stable formations, calves positioned near mothers, juveniles learning by observation. Hunting strategies are refined through participation. Young orcas practice positioning, mimic tail slaps, and respond to vocal cues. Over time, individual skill integrates into collective competence. The pod functions as both family and tactical unit. Knowledge accumulates, passed from elder females to descendants, ensuring continuity of complex behaviors. As dusk falls and the water column darkens, the pod surfaces briefly, exhaling in synchronized bursts before descending again. Beneath them, a scattering layer of fish begins its nightly ascent. The orcas adjust, some diving beneath the layer, others maintaining lateral positions. Echolocation clicks intensify, mapping density. The plan unfolds without visible signal. There is no chaos, no wasted motion. Each surge, each turn, contributes to a shared objective. In the end, the ocean's surface may reveal only faint ripples and the brief flash of black and white bodies. The true drama occurs below, in three-dimensional space, structured by sound and intention. Intelligence here is not an abstract trait, but a survival mechanism that shapes the behavior of entire ecosystems. By compressing fish schools, manipulating movement, and sharing roles, orcas influence prey distribution and even nutrient cycling through their feeding patterns. One predator is undeniably powerful. A plan is transformative. In the deepening blue where light fades and pressure mounts, it is not the sharpness of teeth that defines the orca's dominance, but the capacity to think collectively, to adjust acoustically, and to pursue prey beyond the comfort of the surface. In this realm, teamwork outweighs raw speed, and strategy becomes the most formidable weapon in the sea. On the open seafloor, time moves differently. There are long stretches of quiet, of drifting sediment, and slow currents that carry little more than microscopic detritus. Then, without warning, something large descends. A fish wounded in the upper layers succumbs and sinks. A squid, exhausted from a failed escape, drifts downward in stillness. A carcass falls from the productive world above and lands with a muted thud against sand or rock. In deep and bottom ecosystems, these moments are not minor events. They are windfalls, jackpots in a system where energy is scarce and rarely arrives in concentrated form. The first to notice is often not the swiftest predator, but the most connected scavenger. And on the seafloor, that means crabs. At first, the carcass lies alone, a dark silhouette against pale sediment. Within minutes, subtle movement begins at its edges. Antennae rise from burrows. Legs extend cautiously from beneath ledges. Chemical signals, released immediately upon death or injury, spread outward in invisible plumes. Dissolved amino acids and other organic compounds travel with the current, forming gradients that radiate across the substrate. Crabs do not need sharp vision to interpret these cues. Their antennae and specialized sensory hairs detect chemical concentrations with precision. In this world, scent is a map. A single crab approaches first, claws raised not in threat but in testing readiness. It circles the fallen body, probing with chelae, assessing softness and access points. Within moments, another arrives, then another. From beneath stones and out of narrow fissures, they converge. What appears as individual opportunism rapidly becomes collective action. There is no central coordination, no signal flare, yet the effect resembles organized mobilization. The seafloor cleanup army has assembled. Numbers are their weapon. A solitary crab might struggle to open thick skin or dislodge embedded tissue. A dozen working simultaneously create leverage and disruption. One clamps onto a fin and pulls backward. Another wedges a claw into a soft joint. Smaller individuals exploit openings created by larger ones. The carcass, once intact, begins to fragment under the cumulative force. Speed is not the defining characteristic here. Overwhelming presence is. In deeper waters where temperature remains cold and metabolic rates are lower, crabs conserve energy between such events. They remain largely hidden during periods of scarcity, minimizing movement to reduce predation risk and caloric expenditure. When a jackpot arrives, the sudden influx of energy justifies rapid mobilization. This feast and famine rhythm shapes their behavior. The ability to detect food quickly and arrive en masse determines survival across lean intervals. The scene grows increasingly complex as more crabs join. Larger individuals assert temporary dominance over prime feeding spots, using claws to shove rivals aside. Smaller crabs adapt by targeting peripheral tissues or slipping beneath the carcass to access softer internal organs. Competition exists, but it does not prevent participation. The resource is substantial enough to support many, and delay could mean loss to other scavengers such as fish, or even larger predators attracted by the same scent plume. In abyssal regions, where sunlight never penetrates and organic input is sporadic, such carcasses are transformative events. Deep-sea crabs may traverse considerable distances in response to chemical signals. Their elongated legs allow efficient walking across soft sediment, minimizing sinking. The density of crabs around a carcass can escalate rapidly, forming a living carpet of armored bodies. The carcass itself becomes obscured, consumed beneath layers of movement. This collective feeding behavior is not merely opportunistic indulgence. It is fundamental to the abyss economy. Without scavengers capable of rapidly dismantling large organic inputs, nutrients would remain locked within decaying bodies, releasing slowly and unevenly. Crabs accelerate this recycling. By tearing flesh into smaller fragments and consuming tissues directly, they convert complex organic matter into energy that enters their own biomass. Waste products released back into the sediment enrich microbial communities. Microbes, in turn, break down remaining material into forms usable by other organisms. The cleanup army thus serves as a bridge between episodic abundance and sustained ecosystem function. In nutrient-poor environments, preventing energy from stagnating is critical. Crabs act as processors, ensuring that no jackpot goes to waste. Their digestive systems are adapted to handle a range of materials, from fresh muscle to partially decomposed tissue. Enzymes break down proteins and lipids efficiently, even at lower temperatures characteristic of deep water. The swarm also influences predation patterns. Large predators may hesitate to engage when dozens of claws are already entrenched in a carcass. The mass of moving exoskeletons creates a shifting barrier, discouraging access unless the predator is significantly larger. In some cases, fish attempt to dart in and snatch fragments, only to be confronted by snapping chelae. The cleanup army does not defend territory in a coordinated sense, yet its density provides incidental deterrence. Beyond carrion, crabs exploit other windfalls. Trapped animals ensnared in fishing gear or caught in natural crevices may attract similar swarms. Even fallen plant matter from coastal regions drifting into deeper zones becomes a resource. The unifying theme is rapid response to rare opportunity. This responsiveness requires sensitivity not only to chemical cues, but also to vibration. The lateral motion of a descending object can generate subtle pressure waves detected by nearby crabs, prompting exploratory movement even before scent disperses fully. Thermoregulation in crabs aligns with their ectothermic physiology. Cold water slows metabolism, extending the interval between feeding events, but also reducing energy demands. This balance enables survival in deep and temperate regions alike. Some species exhibit seasonal migrations, moving into shallower waters during warmer months and returning to deeper zones as temperatures drop. These movements align with shifts in prey availability and reproductive cycles. During breeding seasons, females carrying eggs may alter their feeding patterns, prioritizing energy intake to support embryonic development. Molting, as with lobsters, introduces vulnerability. The rigid exoskeleton must be shed for growth to occur. In the context of swarm behavior, molting presents additional risk. A soft-shelled crab within a feeding aggregation could become prey to its own kind. Timing is therefore crucial. Many crabs molt in secluded shelters, away from competitive gatherings. The hardened shell, once restored, re-enters the arena of the cleanup army. The cinematic quality of a swarm feeding event is both chaotic and purposeful. Claws rise and fall rhythmically. Legs interlock and reposition. Fragments of tissue drift upward before being seized again. The carcass diminishes visibly within hours, reduced from a substantial form to scattered bones or cartilage. What remains becomes habitat for smaller invertebrates, continuing the chain of utilization. Irony lies in their unglamorous reputation. Crabs are rarely celebrated as apex predators or graceful navigators. Yet in the context of the seafloor, they are indispensable agents of renewal. Without their rapid intervention, large inputs of organic matter might decompose slowly, creating localized anoxic conditions detrimental to other life forms. By dispersing and consuming material quickly, they maintain balance. As currents shift and the carcass disappears, the swarm thins. Individuals retreat toward familiar shelters, their abdomens distended with new reserves. The seafloor returns to apparent quiet. Yet beneath that calm lies a network of sensors and instincts primed for the next signal. In the abyss and along darkened bottoms, scarcity is constant, but opportunity arrives unpredictably. When it does, the cleanup army mobilizes with relentless efficiency. Their dominance does not stem from speed or singular strength. It arises from multiplicity and responsiveness. In numbers, claws become a collective force. In darkness, scent becomes the call to assemble. The seafloor cleanup army transforms death into sustenance, and sustenance into continuity. In a realm where energy is the most valuable currency, crabs ensure that nothing valuable remains idle for long. When the sun sinks below the horizon and the ocean loses its sharp edges, the hierarchy of specialization begins to blur. Coral reefs that glittered in structured daylight dissolve into silhouettes. Sandbanks flatten into indistinct plains. Currents shift with cooling air, and suspended particles thicken the water column. In this dim, unstable light, certainty becomes rare. Prey animals that rely on color, contrast, and clear sightlines find their information degraded. In this hour, the tiger shark does not rush. It does not need to. The changing water works in its favor. The tiger shark is often described in simple terms as large, opportunistic, and broad in diet. But in low-light environments, that broadness is not incidental. It is a strategy. In daylight, certain predators depend on narrow hunting techniques, targeting specific prey types with specialized tactics. As visibility declines and the distribution of prey becomes unpredictable, rigidity becomes a liability. The tiger shark thrives because it is not constrained by narrow preferences. Its diet spans fish, sea turtles, seabirds, rays, smaller sharks, carrion, and even inedible debris, mistaken in chaotic conditions for potential nourishment. In the darkness of night, or the turbulence following a storm, opportunities arise randomly. A predator that hesitates to evaluate each potential target risks missing rare calories. The tiger shark's less selective feeding behavior allows it to exploit a wide range of scenarios where more specialized predators might falter. The water at dusk is rarely uniform. Waves reflect the last slivers of light in fractured bands that ripple across the shark's body. The vertical bars along its flanks, more visible in younger individuals, are not decorative markings, but structural camouflage. In moving light, Those stripes disrupt the outline of the body, breaking up the shark's form into fragmented patterns that mirror the shifting glare above. As the shark swims beneath a surface textured by wind and swell, the alternating shadows conceal its mass. From below, prey looking upward toward dim surface light perceives distortion rather than a clean silhouette. The stripes interfere with edge detection, a fundamental aspect of visual processing in many marine animals. In water where clarity is compromised, disrupting shape is often more important than blending color. Stealth in dim water depends not only on visual camouflage, but also on controlled motion. The tiger shark moves with a measured rhythm, its broad head sweeping slightly from side to side. This motion is not aimless, it enhances sensory sampling. Along its snout and around the head are clusters of ampullae of Lorenzini, electroreceptive organs capable of detecting minute electrical fields generated by muscle contractions in prey. Even when visibility drops to near zero in murky water, electrical signals persist. A buried stingray, invisible beneath sand disturbed by storm currents, cannot conceal the faint bioelectric field produced by its respiratory movements. The tiger shark, cruising low over the seabed, senses this signal and adjusts course. The lateral line system, sensitive to low-frequency vibrations, complements electroreception. In chaotic conditions following heavy weather, debris tumbles and water pulses unpredictably. Prey fish may scatter, their schooling behavior disrupted by turbulence. In such disorder, specialized predators reliant on coordinated prey movement struggle. The tiger shark, less dependent on structured schooling patterns, benefits from the confusion. Individual prey separated from groups become vulnerable. The shark reads vibration patterns, distinguishing between inanimate drift and purposeful swimming. It does not require perfect clarity. It requires only enough signal to act. Storms introduce additional dynamics. Heavy rainfall can reduce salinity in surface layers, creating stratification and mixing events that alter the distribution of organisms. Nutrients stirred from the seafloor may attract smaller fish, which in turn draw larger predators. In these turbulent periods, the ecosystem's usual order is suspended. The tiger shark's tolerance for variable conditions gives it an advantage. Its physiology accommodates a range of temperatures and salinities, allowing it to patrol estuaries, coastal shallows, and offshore waters with equal competence. Where other large sharks may prefer clearer, open water, the tiger shark ventures into zones of reduced visibility without hesitation. Thermoregulation plays a subtle but important role in this flexibility. As an ectothermic species, the tiger shark's internal temperature aligns closely with surrounding water. However, its size provides a degree of thermal inertia, slowing rapid fluctuations. In nighttime conditions when surface waters cool, the shark's large body retains heat slightly longer than smaller fish, maintaining muscular efficiency during transitional hours. This advantage is not as pronounced as the regional endothermy seen in some other shark species, but it contributes to sustained performance when environmental temperatures shift. Generalist feeding behavior often carries a negative connotation in human interpretation, but in ecological terms, it represents resilience. In an environment where prey availability fluctuates unpredictably due to seasonal migrations, storm events, and daily light cycles, a predator that can exploit diverse food sources maintains stability. The tiger shark's jaw structure supports this versatility. Serrated, triangular teeth allow it to slice through turtle shells, sever fish, or tear into carrion. The digestive system tolerates a range of materials, though indigestible debris is sometimes expelled later. This breadth of capability reflects adaptation to randomness. Nighttime transitions amplify these traits. As darkness spreads, diurnal fish seek shelter, while nocturnal species emerge. The water column reorganizes yet again. Some prey ascend, others descend. In this moment of exchange, information is incomplete. Visual hunters must recalibrate. The tiger shark, already attuned to low-light cues, navigates the shift fluidly. Its eyes, adapted to detect contrast rather than color, continue to function effectively in dim conditions. The tapetum lucidum enhances light sensitivity, reflecting photons back through the retina to maximize detection. Combined with electroreception and vibration sensing, The shark operates with multi-layered awareness. There is an understated irony in the tiger shark's reputation. Its imposing size and broad diet have earned it notoriety, yet in ecological context, it often functions as a stabilizer in chaotic systems. By consuming weak, injured, or dead animals, it reduces disease transmission. By preying on species that surge in number after disturbances, it dampens population spikes. In murky estuaries where human perception might see only hazard, the shark's presence integrates into nutrient cycles and population control. As night deepens, the ocean's surface loses its glare entirely. The stripes along the shark's flanks fade into uniform shadow. A school of fish, disoriented by residual storm currents, drifts closer to shore. Some individuals break formation, chasing smaller prey stirred by sediment. The tiger shark approaches without abrupt acceleration. Its broad head sweeps again, electroreceptors sampling, lateral line registering vibration. A single fish strays too far from cover. The shark accelerates in a short, controlled burst. The strike is decisive, but not extravagant. In dim water, excess motion would announce presence to other prey. Efficiency remains paramount. The connection to deeper waters lies not in physical descent to abyssal depths, but in behavioral adaptability to darkness and disorder. In ecosystems where environmental stability declines, whether due to natural storms or broader climatic shifts, generalists often outcompete specialists. The tiger shark exemplifies this principle in marine form. It thrives when systems become unpredictable, when sediment clouds obscure vision, when prey distributions fragment. While other predators may rely on precision tuned to stable conditions, the tiger shark capitalizes on variability itself. The night shift of the ocean does not belong exclusively to any single species. It is a period of reorganization, of overlapping migrations and altered hierarchies. In that shifting framework, the tiger shark's dominance emerges not from speed alone, but from tolerance and flexibility. It does not require perfect clarity, a specific prey type, or a narrow window of opportunity. It requires only the presence of life in motion and the willingness to exploit it. As dawn approaches and the first pale light filters through the water, the shark's outline regains contrast. The stripes reappear faintly against grey-blue skin. The ecosystem begins its daytime order once more. Yet the hours of darkness have revealed a truth about survival in fluctuating environments. Adaptability outweighs specialization when information degrades. In dim water and chaotic currents, the tiger shark's broad appetite and sensory integration transform uncertainty into opportunity. It is not merely a predator of prey, but a beneficiary of disorder, moving steadily through murk where others hesitate, shaped by evolution to endure when clarity disappears. When daylight drains from the shallows and the reef exhales into shadow, the seafloor becomes a different country. Shapes that were vivid and sharply defined soften into muted contours. Crevices deepen into narrow black slits between rock and coral rubble. Fine particles drift in slow suspension, catching the last available photons before dissolving into indigo. The abyss does not always require crushing depth. Sometimes it is simply the absence of light across a landscape already built for concealment. On this dim bottom, where vision loses authority, the lobsters emerge. During the day, they remain hidden, wedged tightly into cavities with only antennae extending outward, tasting and sampling the water for chemical cues. Night alters the equation. Darkness reduces the dominance of sight-based predators such as certain reef fish and birds. In that visual decline, other senses rise to primacy. The lobster's world is constructed less from images and more from gradients of scent and vibration. Its antennae sweep forward in wide arcs, long and flexible, brushing against rock and probing open sand as it leaves its shelter. Each movement is deliberate. The antennae are not simply tactile feelers. They are lined with sensory hairs capable of detecting dissolved chemical signals, minute traces left by injured prey or decomposing matter. The lobster does not rush into open terrain. It advances in measured steps, armored body low to the substrate. Its exoskeleton, hardened with chitin and reinforced by calcium deposits, forms a protective shell that covers the cephalothorax and abdomen. The surface is ridged and spined, discouraging grasp by opportunistic predators. In silhouette, it resembles a compact armored vehicle navigating uneven ground. Yet this armor is both strength and burden. It cannot expand. Growth demands periodic shedding, a process that transforms the armored raider into something dangerously fragile. Before considering vulnerability, the night hunt unfolds. The lobster's compound eyes, though limited in detail compared to vertebrate vision, are sensitive to low light. Reflective layers enhance photon capture, allowing perception in dim conditions. However, sight remains secondary to chemical detection. When a small mollusk lies partially buried in sediment, its slow respiration releases faint chemical plumes. Currents distribute these plumes unevenly, forming invisible trails. The lobster pauses, antennae elevated and then lowered toward the source, adjusting direction based on gradient strength. Its sensory world is not mapped in lines and edges, but in concentrations and intensities. Claws become instruments of negotiation. In species possessing asymmetrical claws, one may be specialized for crushing, while the other is designed for cutting. The crushing claw, thicker and more robust, can exert substantial force capable of breaking shells. The cutting claw, narrower and edged with serrations, handles softer tissues and precise manipulation. When encountering prey, the lobster first secures it with the smaller claw, testing resistance. If the prey attempts escape, the larger claw delivers a decisive grip. There is no dramatic chase. The lobster relies on patience and leverage. This strategy suits the seafloor environment. Energy expenditure must be balanced against caloric return. Cold nighttime waters slow metabolism, reducing the need for constant feeding, but also limiting sustained bursts of activity. The lobster's ectothermic physiology aligns internal temperature with ambient water. In cooler conditions, muscle contraction slows slightly, yet so does the prey's reaction speed. The equilibrium favors a predator that can afford to wait. Interactions with other bottom dwellers introduce further complexity. Octopuses, as discussed previously, are adept at infiltrating crevices and extracting lobsters from shelters. In response, lobsters may cluster in groups within shared dens, their antennae extending outward like defensive lances. When threatened, they can produce rasping sounds by rubbing parts of their exoskeleton together, creating vibrations that may deter predators momentarily. Such acoustic displays illustrate that even heavily armored species maintain layered defense strategies. Yet the most precarious chapter of a lobster's life arrives not during predation, but during growth. To increase in size, the lobster must molt, shedding its rigid exoskeleton in a process known as ecdysis. Prior to molting, the animal reabsorbs some calcium from the existing shell and stores it internally in small structures called gastroliths. When the old shell splits along predetermined seams, the lobster pulls itself free, emerging with a new exoskeleton that is soft and pliable. In this state, it resembles a shadow of its armored self, limbs flexible, claws lacking rigidity. The timing of molting is influenced by environmental factors, including temperature and food availability. Warmer water may accelerate metabolic processes, leading to more frequent molts during juvenile stages. However, each molt represents a period of acute vulnerability. Without hardened armor, the lobster cannot defend itself effectively against fish, octopuses, or even larger conspecifics. The abyss punishes weakness immediately. A soft-shelled lobster must seek shelter rapidly, often remaining hidden for days, while the new exoskeleton hardens through mineralization. During this hardening phase, the lobster's behavior shifts from assertive foraging to cautious immobility. It wedges into the tightest crevices available, minimizing exposure. Muscle contractions are restrained to conserve energy and avoid attracting attention. Chemical cues in the water may betray its presence, but remaining still reduces detection likelihood. The process of hardening involves depositing calcium into the new cuticle, restoring rigidity gradually. Only once the armor regains sufficient strength does the lobster resume its nocturnal patrols. The cyclical transformation from armored tank to soft prey underscores an ecological balance. The same exoskeleton that enables survival during most of the year demands periodic abandonment. Growth cannot occur without temporary surrender of defense. In evolutionary terms, this trade-off persists because the long-term benefits of increased size and reproductive capacity outweigh the short-term risks. Larger lobsters may deter certain predators and compete more effectively for territory. Yet each molt is a gamble against predation. Night on the bottom amplifies both power and peril. As currents sweep across sandflats and reef slopes, scents travel in shifting plumes. A recently molted lobster, even hidden, may emit subtle chemical signals associated with soft tissue and stress. Predators attuned to these cues may intensify their search. The armored raider, for a brief window, becomes the hunted. Beyond individual survival, lobsters play a significant role in benthic ecosystems. By preying on mollusks and smaller crustaceans, they influence species composition and nutrient cycling. Their burrowing and shelter-building activities modify microhabitats, creating niches for smaller organisms. Even discarded molted shells contribute calcium back into the system, becoming substrate for algae and invertebrates. As midnight deepens and the water grows still, a fully armored lobster resumes its patrol. Antennae sweep, claws poised. The exoskeleton glints faintly under starlit surface, shimmer filtered down through meters of water. It navigates the terrain with slow assurance, testing rock and sand with equal scrutiny. To an observer, the motion may seem mechanical, but beneath the shell is a living organism finely tuned to darkness. The cinematic contrast between strength and fragility defines the lobster's existence. One night, it moves like an armored tank, claws negotiating every encounter with deliberate force. On another, hidden in a crevice, it waits as a soft-bodied creature, hoping the ocean overlooks its weakness. The abyss of night does not discriminate. It rewards sensory acuity and punishes vulnerability without hesitation. In this bottom world where light fails and scent guides direction, the lobster embodies resilience shaped by compromise. Its antennae read chemical maps invisible to eyes. Its claws resolve conflicts in measured grips. Its armor protects but demands sacrifice. And in the silent hours when the reef sleeps, the armored night raider advances, aware that survival depends not only on strength, but on timing the fragile intervals when strength must be rebuilt. There is no forest to vanish into in the midwater column, no coral labyrinth to weave between, no rocky crevice to claim as refuge. Between the sunlit surface and the true abyss lies an immense, open architecture of water, where concealment is rare and exposure is constant. In this suspended landscape, survival depends less on hiding behind structure and more on rewriting the rules of motion itself. A squid, drifting in this column of near emptiness, is never truly still. Even when hovering, subtle pulses ripple through its mantle, fine adjustments that maintain position in a fluid environment where buoyancy is neutral and gravity exerts only indirect influence. Here, speed is not an accessory to life. It is the first defense, the first offense, and often the only boundary between survival and consumption. The squid's body is built around a muscular tube known as the mantle, and this mantle is more than a housing for organs. It is an engine. Water is drawn into the mantle cavity through a collar opening, and then expelled forcefully through a narrow funnel called the siphon. Each contraction of the mantle compresses the internal cavity, generating a jet of water that propels the animal in the opposite direction. This principle is simple in physical terms. Expelled mass produces forward thrust. But in biological execution, it is extraordinarily refined. The mantle wall is composed of circular and radial muscle fibers arranged to allow rapid contraction and equally rapid refilling. In routine movement, contractions are measured and economical, allowing the squid to hover or glide. In crisis, those same muscles can fire in rapid succession, producing explosive bursts that carry the animal backward at remarkable speed. Unlike many fish which rely on oscillating tails for sustained cruising, squid are specialists in acceleration rather than endurance. Their bodies are streamlined and tapered, reducing drag during forward or backward surges. Fins positioned along the mantle can provide subtle steering and stability. But during a burst escape, they become secondary to the siphon-driven jet. The direction of propulsion is not fixed. The siphon can pivot, altering the angle of expelled water. This allows sudden changes in trajectory that are disorienting to predators. In an environment without obstacles, unpredictability becomes a form of shelter. A pursuing fish or marine mammal must constantly recalculate direction, and in the fractions of seconds required to adjust, distance may widen enough for escape. Yet the squid is not merely a fleeing organism. Its anatomy reveals dual intentions. At the front of its body extend 8 arms and 2 longer tentacles. These appendages are often misunderstood as interchangeable, but their functions are distinct. The 8 arms are relatively shorter, lined with suckers along much of their length, and are used for control and manipulation. They secure prey, guide it toward the beak, and maintain grip during struggle. The 2 tentacles are longer and often retractable, terminating in specialized clubs equipped with concentrated arrays of suckers or hooks. These tentacles are capture tools, designed to shoot forward rapidly and seize prey at a distance before drawing it inward. This division of labor reflects a balance between reach and restraint. The tentacles initiate contact. The arms consolidate it. In open water, where prey may detect approach from multiple angles, the squid's strategy often relies on ambush combined with acceleration. Its skin is layered with chromatophores, pigment, containing cells that expand or contract under neural control, allowing rapid shifts in coloration and pattern. Beneath these lie iridophores and leucophores, reflective cells that can alter brightness and sheen. In brighter upper waters, this system enables camouflage against shifting backgrounds. In dimmer zones, pattern changes can create flickers that disrupt an observer's ability to judge distance or direction. The squid's nervous system, proportionally large among invertebrates, coordinates these color changes with muscular action. A lunge is often accompanied by a flash or darkening, a momentary sensory overload for prey. When threatened by larger predators such as tuna, sharks, or toothed whales, the squid must rely on its capacity for burst escape. The mantle contracts powerfully, expelling water in a focused jet that propels the body backward, while the head and arms face the direction of travel. This orientation allows the squid to monitor the threat even while retreating. Sudden, angular shifts in siphon orientation can produce zigzag trajectories that challenge the pursuit of animals optimized for more linear chases. However, such bursts are metabolically expensive. Rapid muscle contractions consume oxygen and generate waste products that must be cleared. The squid's design reflects a compromise. It can generate extraordinary speed, but only in short intervals. In the open midwater, survival often hinges on whether that short interval is sufficient. As depth increases and light diminishes, the dynamics of pursuit shift from predominantly visual to increasingly reliant on movement detection, and for some predators, echolocation. In this near-black realm, the squid's ink becomes more than a simple cloud. In shallower waters, ink functions primarily as a visual screen, a dark plume that obscures the animal's retreat. In deeper waters, where light is scarce, ink assumes a different role. Rather than merely blocking sight, it creates a discrete object in the water column, a pseudomorph, shaped roughly like the squid itself. This concentrated mass of ink can momentarily retain form, especially when expelled with mucus components that increase cohesion. A predator tracking movement or faint bioluminescent cues may lock onto this sudden target, while the squid executes a rapid directional shift. Darkness amplifies the effectiveness of such misdirection. In low-light environments, predators often rely on detecting contrast or movement against a uniform background. When the squid releases ink and immediately accelerates in a new direction, the original motion signal vanishes. The predator, faced with a sudden stationary dark mass and the absence of continued motion cues, must recalibrate. In the seconds required to differentiate ink from flesh, the squid may have moved beyond immediate reach. This strategy illustrates an important evolutionary principle. In environments where cover is absent, confusion itself becomes habitat. The abyss intensifies these interactions. As depths approach regions where sunlight never penetrates, organisms enlarge their sensory apparatus. Squid inhabiting deeper zones often possess disproportionately large eyes relative to body size. These eyes are adapted to detect minimal light, including faint bioluminescent emissions from other organisms. The retina contains photoreceptors optimized for low light sensitivity rather than color discrimination. In such darkness, Detecting the silhouette of a predator against residual downwelling light or the flash of a bioluminescent lure can determine survival. Predators, in turn, evolve larger eyes or alternative sensory systems to detect subtle disturbances. This reciprocal escalation constitutes a deep-sea arms race. As predators become more adept at detecting motion or faint glows, prey evolve enhanced speed, improved camouflage, or more elaborate decoys. Some deep-sea squid species grow to considerable sizes, potentially as both defensive deterrents and competitive advantages in capturing scarce prey. Larger body size can store more energy and sustain longer migrations through nutrient-poor waters. However, increased size also demands greater oxygen and exposes a larger silhouette. The balance between growth and concealment reflects pressures unique to the abyssal environment. In this context, speed is not merely about outrunning an attacker, it is about crossing vast, food-poor expanses efficiently. Many squid undertake vertical migrations, ascending toward richer feeding layers at night and descending during daylight to avoid visually oriented predators. This daily movement exposes them to changing temperatures and pressures, requiring physiological flexibility. Their blood contains hemocyanin, a copper-based oxygen carrier that functions effectively in cold, low-oxygen conditions typical of deeper waters. As they ascend into warmer layers, metabolic rates increase, enabling more active hunting. As they descend, metabolism adjusts, conserving energy in colder, darker strata. The open ocean's apparent emptiness conceals constant negotiation between visibility and invisibility, speed and stillness. A squid drifting at depth may appear vulnerable, yet its body is primed for instantaneous transformation from passive to explosive. Its tentacles can extend with startling velocity, capturing fish that stray too close. Its arms secure and guide prey toward a sharp, parrot-like beak capable of slicing through flesh. Within its mouth lies a radula, a rasping structure that processes captured tissue. The same appendages that manipulate prey also brace during escape, streamlining along the body to reduce drag when maximum acceleration is required. There is a subtle irony in the squid's dual identity. It is both weapon and evasion system, engineered to strike and to vanish. In an environment without physical cover, it manufactures opportunity through physics and neurology. Jet propulsion provides the burst necessary to disrupt a chase. Ink creates ambiguity, where clarity would mean death. Chromatophores rewrite appearance in fractions of a second. Enlarged eyes absorb faint light that might signal threat. Every adaptation speaks to a life lived in open exposure. As predators such as sperm whales descend with acoustic precision, the squid's strategy must counter a different sensory mode. Sudden directional shifts can alter the echo profile, complicating tracking. Ink clouds may distort acoustic reflections briefly, adding noise to an already complex signal field. While such measures do not render the squid invulnerable, they demonstrate that even in the deepest waters, prey species are not passive participants in predation. They evolve mechanisms that exploit the limitations of their hunters' senses. In the midwater column, where there are no rocks to hide behind and no plants to blend into, survival depends on mastering space itself. The squid's body is a compromise between hydrodynamic efficiency and muscular explosiveness, between grasping arms and striking tentacles, between visibility and disappearance. Its existence reveals that in the open ocean, speed is not simply about velocity measured across distance. It is about timing, misdirection, and the capacity to become momentarily unreadable in a world where detection is relentless. Within this immense dark expanse, the squid embodies an evolutionary answer to exposure. It cannot rely on terrain, so it manipulates perception. It cannot sustain endless pursuit, so it specializes in decisive bursts. It cannot prevent predators from evolving sharper senses, so it evolves larger eyes, faster muscles, and more convincing decoys. In the abyssal arms race, disappearance is as powerful as aggression, and confusion is a weapon sharpened by darkness. There are places in the ocean where the light is generous, but the truth is not. Sand flats stretch outward in pale expanses, rippled by current and wind, broken only by the faint outlines of buried life. At first glance, they appear simple, almost empty, like a blank page. Yet this apparent openness conceals a different kind of abyss. Here, prey is not suspended in mid-water or silhouetted against glare. It is hidden beneath sediment, pressed into the seabed, camouflaged so completely that even a trained human eye would struggle to detect a single outline. On these flats, vision becomes unreliable, and deception is everywhere. This is where the hammerhead shark excels, not by seeing more, but by sensing what sight cannot reveal. The most striking feature of the hammerhead is the cephalofoil, the laterally expanded head that stretches outward like a wing. It is not ornamental excess. Embedded across its broad surface are thousands of electroreceptors known as the ampullae of Lorenzini. These jelly-filled canals connect surface pores to sensory cells capable of detecting minute electrical fields. Every living organism generates faint electrical signals as muscles contract and nerves fire. These signals are weak, often measured in microvolts, and dissipate quickly in open water. Yet in close proximity, particularly near the seafloor where buried prey cannot easily shield their bioelectric output, they become detectable to a predator equipped to read them. Electroreception is often misunderstood as mystical or exaggerated, but its function is mechanical and precise. When a ray lies buried beneath sand, its gill movements continue to pump water for respiration. The muscles involved in that rhythmic motion produce electrical activity. The heart beats. Nerves transmit impulses. Though the ray's body may be invisible under a thin layer of sediment, its electrical presence persists. The hammerhead sweeps its head side to side as it cruises just above the substrate, effectively widening the sensory field. Each lateral movement samples a broader swath of sand, increasing the likelihood of detecting concealed life. Sand flats resemble an abyss in more ways than one. Visibility may be reduced by suspended sediment stirred by currents or by the shark's own movement. Sunlight reflects off the pale surface, creating glare that obscures subtle depressions. Prey species rely heavily on camouflage here. Stingrays, for example, flatten their bodies and cover themselves with sand, leaving only their spiracles and eyes exposed. Flatfish align their pigmented upper surfaces with surrounding tones, becoming indistinguishable from the seabed. In this environment, visual predators struggle. Even if a ray is partially visible, its outline blends seamlessly into the rippled patterns of the substrate. The hammerhead's approach renders this camouflage incomplete. It does not depend on contrast or shape recognition alone. As it passes over a seemingly empty patch of sand, the electroreceptors register anomalies. The distribution of electric fields across the cephalofoil provides spatial information. By comparing signal strength across left and right extensions of the head, the shark can triangulate the source with remarkable accuracy. The wide separation of sensory pores enhances directional resolution, allowing the predator to localize prey even when visual confirmation is minimal. The shark's eyes, positioned at the ends of the cephalofoil, also provide a broader visual field than that of many other sharks. This arrangement offers partial binocular overlap and increased depth perception in certain orientations. However, in sandflat hunting, the eyes serve as confirmation rather than primary detection tools. The real advantage lies in electrical mapping. The head becomes a scanning instrument, gliding low over the sediment, reading signals invisible to any other sense. Once a target is identified, the behavior shifts from detection to control. The hammerhead often accelerates in a short, decisive movement and uses its head to press the prey into the sand. This pinning action is not incidental. Stingrays possess venomous barbs capable of inflicting serious injury. By forcing the ray's body against the substrate with the broad surface of the cephalofoil, the shark restricts the ray's ability to whip its tail upward. The flattened head acts like a lever and shield simultaneously. With the prey immobilized, the shark can maneuver to bite strategically, often removing sections of the pectoral fins to disable the ray further before consuming the central body. The mechanics of this press reveal a balance between anatomy and behavior. The cephalofoil distributes pressure over a larger area, reducing the risk of penetration from the ray's barb. Meanwhile, the shark's muscular body provides the force necessary to overcome the ray's attempts to flap free. It is a confrontation shaped by evolution on both sides. Rays evolve to bury and defend. Hammerheads evolve to detect and neutralize. On sandflats, the outcome often favors the hunter that can perceive what lies hidden. Electroreception also assists in detecting other prey types concealed within sediment, including small fish and crustaceans. The hammerhead's sensory acuity allows it to hunt during periods of low light or in turbid water when visibility is compromised further. At dusk or after storms, when sediment clouds the water column, many predators lose efficiency. The hammerhead, less dependent on clarity, continues its patrol. Its advantage increases as visual information decreases. There is a broader ecological implication in this dynamic. Sandflats support diverse communities of invertebrates and small fish that recycle nutrients and maintain sediment structure. By preying on buried rays and other species, hammerheads influence the composition of these communities. Removing rays can alter predation pressure on smaller organisms, reshaping benthic food webs. Thus, the act of detecting hidden electricity reverberates through the ecosystem. The phrase that captures this interaction is stark in its simplicity: hiding under sandworks until someone hunts electricity. Camouflage is a powerful survival strategy when predators rely on sight. It becomes less effective when predators evolve new sensory modalities. The hammerhead exemplifies this escalation. Prey species may attempt to minimize electrical output by reducing movement, but respiration cannot cease indefinitely. Life produces current, and the hammerhead has learned to read it. Thermal conditions on sandflats can vary significantly between day and night. Shallow waters warm under sunlight and cool after sunset. As ectotherms, hammerheads align their internal temperature with surrounding water. However, their large body mass slows rapid temperature shifts, maintaining functional muscle performance across transitional periods. This stability supports extended foraging sessions during changing light conditions. Combined with electroreception, it allows the shark to exploit windows when prey behavior shifts in response to temperature and light. In some regions, hammerheads aggregate in groups, yet hunting on sandflats is often solitary or loosely coordinated. Even without coordinated group tactics, the sensory architecture of each individual provides sufficient precision. The shark's sweeping head motion creates a rhythm across the seabed, a silent metronome sampling the electrical landscape. To an observer, the movement appears almost casual. Beneath that surface is a constant flow of data, interpreted and acted upon in fractions of a second. As the shark glides onward, the sand behind it remains undisturbed, except where a sudden press and flurry mark a successful capture. The flat surface resumes its deceptive calm. Rays settle again beneath thin layers of sediment. Flatfish align with ripple patterns. Life hides, yet the vulnerability remains. Every heartbeat, every muscle contraction radiates a signal. In a world where sight can be deceived, electricity cannot lie. The hammerhead's design challenges assumptions about predation based solely on teeth or speed. Its dominance on sandflats arises from sensory innovation and mechanical application. The cephalofoil is not an eccentric flourish of evolution, but a platform expanding the range and resolution of perception. By sweeping that platform across the seabed, the shark transforms invisible signals into actionable targets. The press that follows is not dramatic, but it is decisive. On these pale plains where deception thrives, the abyss is not a matter of depth, but of concealment. Prey invest in camouflage and burial. The hammerhead invests in perception beyond sight. The result is an arms race conducted beneath the surface, measured not in visible pursuit, but in microvolt detection. As long as life pulses beneath sand, it emits a trace. And as long as that trace exists, the hammerhead will continue to patrol, reading the seafloor not with eyes alone, but with electrical vision. On a rocky slope where the reef gives way to deeper water, the light thins into a muted haze. Shadows lengthen across boulders and coral heads, and crevices deepen into pockets of uncertainty. In this transitional space between brightness and obscurity, speed is not always the decisive advantage. Movement can betray as easily as it can empower. Here, among scattered stones and fractured ledges, an octopus settles into stillness, its body pressed low against the substrate. Its skin shifts in texture and tone, rising into small papillae that mimic the rough surface of rock, then smoothing again as if reconsidering its disguise. The transformation is not decorative. It is strategic. In this dim environment, camouflage is not passive blending. It is calculated misdirection. The octopus is often described as intelligent, but intelligence here is not an abstract concept measured in laboratory tasks. It is embodied in interaction with terrain. Unlike many predators that rely on speed or overwhelming force, the octopus operates through manipulation. Its 8 arms, lined with hundreds of suckers, are not merely appendages for grasping. Each sucker contains chemoreceptors and tactile sensors, allowing the animal to taste and feel simultaneously. In low visibility, where sight becomes unreliable, touch replaces vision as the primary source of information. The arms sweep across rock surfaces and into narrow crevices, mapping contours through contact. Texture, temperature, and chemical traces become data points in a constantly updating model of the immediate world. Hunting begins with exploration rather than pursuit. A small crab, tucked beneath a slab of coral, remains motionless, relying on shadow and stillness for concealment. The octopus approaches not in a straight line but from the side, minimizing the chance of casting a distinct silhouette. One arm slips quietly around the rock's edge, probing for resistance. The suckers adhere lightly, testing surfaces. Another arm follows, forming a partial barrier at the opposite exit. The octopus does not lunge immediately. It constructs a perimeter. This behavior illustrates a fundamental principle of octopus hunting. Terrain becomes an extension of the predator's body. By positioning arms strategically around openings, the octopus reduces escape routes. If the crab bolts forward, it encounters a curtain of suckers. If it retreats, another arm intercepts. In some cases, the octopus may deploy a thin web of membrane that connects its arms, enveloping prey in a flexible net. This webbing does not entangle like fishing gear. It simply increases surface area, making sudden directional shifts more difficult for the prey. Once containment is achieved, the octopus brings the prey toward its beak, a hard, parrot-like structure hidden beneath the mantle. The beak delivers a precise bite, often injecting venom through a salivary gland. The venom contains compounds that immobilize the prey quickly, reducing struggle. The sequence is controlled and methodical. There is little wasted motion. The octopus has effectively turned the environment into a trap, using rock faces and crevices as boundaries within a carefully constructed enclosure. In deeper water, where light diminishes further and sediment clouds visibility, tactile exploration becomes even more critical. The arms extend ahead of the body, fanning outward to sense subtle changes in the substrate. An octopus can detect the faint movement of a buried mollusk or the slight shift of sand caused by a hidden fish. Its skin itself contains light-sensitive cells that respond to brightness levels, assisting in rapid camouflage adjustments even when the eyes provide limited information. In these conditions, the arms function almost as independent agents, each capable of processing local sensory input before relaying signals to the central brain. The octopus nervous system is distributed in a way that reflects this decentralized sensing. A significant portion of its neurons reside within the arms, rather than solely in the central brain. This arrangement allows each arm to coordinate complex movements semi-autonomously. When exploring a labyrinth of rocks, the arms adjust grip and pressure without requiring continuous central commands. This distributed intelligence enhances responsiveness in darkness, where reaction times must be immediate and localized. Camouflage in the octopus extends beyond color change. Specialized pigment cells called chromatophores expand and contract to alter hue, while iridophores reflect light to adjust brightness. Papillae modify skin texture, creating ridges or bumps that mimic surrounding surfaces. However, camouflage also includes behavioral elements. An octopus may align its body orientation with the grain of rock or freeze mid-motion to resemble debris caught in current. In low visibility, the combination of texture, tone, and posture creates ambiguity. Predators scanning the environment may overlook the octopus not because it is invisible, but because it resembles something uninteresting. There are moments when deception becomes active rather than defensive. Some octopuses have been observed imitating other species, adopting patterns and postures that resemble venomous fish or sea snakes. Even without such mimicry, the octopus can produce sudden color flashes that startle potential predators, buying seconds to retreat into a den. The transition from camouflage to display and back again occurs within fractions of a second, reflecting rapid neural control over skin cells. In abyss-like conditions, speed is limited by environment and energy constraints. Chasing prey across uneven terrain wastes oxygen and risks injury. Intelligence replaces speed by preempting the need for pursuit. By blocking exits before initiating capture, the octopus reduces reliance on rapid acceleration. This approach is particularly advantageous in cooler, deeper water, where metabolic rates decline. As an ectotherm, the octopus's internal temperature aligns with ambient conditions. Cooler temperatures slow muscle contraction, but also reduce energy expenditure. A hunting strategy centered on planning and positioning rather than sprinting aligns with this physiological reality. The relationship between octopus and habitat is intimate. Dens are often constructed within natural cavities, reinforced with stones or shells collected and arranged deliberately. These shelters provide protection during daylight or when predators patrol. The act of arranging objects suggests foresight and spatial awareness. In some cases, octopuses have been documented carrying coconut shells or other debris as portable shelters, assembling them later into protective enclosures. Such behavior underscores an ability to manipulate objects in anticipation of future need. In darkness, where sight offers limited guidance, the octopus's arms become a sensory net cast outward. Each sucker grips and releases in rhythmic sequence, sampling the world like fingertips across a keyboard. The tactile map formed by these contacts is rich in detail. The octopus learns the layout of its territory, remembering which crevices harbor prey and which conceal threats. Memory, in this context, is survival. Predators of octopuses include sharks, large fish, and marine mammals. To evade them, the octopus relies on rapid color shifts and sudden jet propulsion, expelling water from its mantle to dart backward. However, such bursts are energy-intensive and reserved for emergencies. The preferred strategy remains avoidance through concealment and careful movement. In dim water, the octopus often blends seamlessly with its surroundings until the threat passes. The ecological role of the octopus extends beyond predation. By consuming crustaceans and mollusks, it influences population dynamics within reef and benthic communities. Shell piles outside dens testify to repeated feeding events, creating microhabitats for smaller organisms that inhabit discarded remains. In this way, the octopus indirectly shapes local biodiversity. As night deepens and the environment quiets, the octopus resumes its methodical patrol. Its arms explore, block, and weave. A small fish darting between rocks may not realize that escape routes have already narrowed. The octopus tightens its enclosure gradually, leaving little opportunity for sudden flight. The final act, delivered by beak and venom, is swift but almost anticlimactic compared to the planning that preceded it. The defining truth in this landscape is stark yet precise. In the abyss, intelligence replaces speed. Where light fades and reaction time shortens, the ability to anticipate and manipulate becomes more valuable than brute force. The octopus embodies this principle in flesh and nerve. It does not overpower its environment. It integrates with it, turning terrain into strategy and darkness into opportunity. In the quiet spaces between rocks and shadow, the brain with 8 locks moves deliberately, solving the problem of survival one calculated grip at a time. In the upper layers of tropical seas, where sunlight fractures into wavering lattices and coral heads glow with chromatic intensity, manta rays appear almost ceremonial in their movements. They circle cleaning stations where smaller fish pick parasites from their skin. They glide near the surface in broad arcs, their cephalic lobes unfurled like open scrolls, guiding plankton into cavernous mouths. In these moments they seem approachable, even gentle. Yet the ocean does not remain a sunlit amphitheater, and neither do mantas confine themselves to it. Beneath the brilliance lies a layered architecture of temperature, density, and current. And it is within this invisible structure that the manta ray reveals a more complex identity. It is not a predator in the traditional sense, but it is an explorer of gradients, a navigator of depth that turns subtle ocean physics into survival. The first descent often occurs without spectacle. A manta ray, having fed in surface waters, tilts its wingtips downward and begins a measured glide. The broad pectoral fins, extending outward like aerodynamic surfaces, generate lift as they beat slowly, then settle into long, unhurried strokes. The water darkens incrementally. Colors mute from turquoise to cobalt to deep indigo. A thermocline may lie ahead, a boundary where temperature shifts abruptly across a thin vertical span. Crossing it can feel like entering a different sea. For many fish, such gradients are obstacles or barriers. For a manta, they are information. Thermoclines influence plankton distribution. Microscopic organisms often accumulate along density layers where currents converge or where nutrients rise from below. These thin, nearly invisible strata can concentrate food in bands suspended mid-water. A manta ray's ability to locate and exploit such bands depends not on speed, but on sensory integration and memory. Its brain, proportionally large for a fish, supports complex spatial awareness. Studies suggest mantas can recognize individual conspecifics and possibly remember locations of productive feeding grounds across seasons. This cognitive capacity becomes critical when the ocean's productivity shifts unpredictably. As the manta descends further, the light diminishes to a diffuse glow. The outline of its body becomes more pronounced against the fading blue. With a wingspan that can rival the width of a small aircraft, the ray transforms into a gliding shadow. From below, its pale underside blends with faint downwelling light. From above, its darker dorsal surface merges with deeper water. This countershading is not incidental. It reduces detection by potential predators such as large sharks or orcas that patrol both above and below. The manta's size offers some protection, but it is not invulnerable. Remaining inconspicuous in transitional light zones reduces risk. Deep glides serve multiple purposes. By descending through water columns, mantas sample temperature gradients and current flows. Cooler water at depth may slow metabolic rate slightly, conserving energy between feeding bouts. Unlike some sharks that generate internal heat to maintain muscle temperature, mantas are ectothermic. Their body temperature mirrors surrounding water. However, their large mass confers thermal inertia, moderating rapid changes. A glide into cooler depths after intense surface feeding may provide physiological recovery, allowing digestive processes to proceed efficiently while reducing surface exposure to predators. Currents, though invisible, sculpt the ocean's architecture. Upwelling zones bring nutrient-rich water toward the surface, fueling plankton blooms. Convergent fronts compress floating debris and microscopic life into narrow lines. A manta ray, navigating these features, is reading the ocean much like a soaring bird reads thermals in the sky. The cephalic lobes at the front of its head, often described simply as feeding structures, also function in steering and channeling flow. When unfurled, they guide plankton-laden water toward the mouth. When rolled inward, they streamline the body for travel. Adjusting these lobes mid-glide allows the ray to fine-tune intake based on density. In deeper water, feeding becomes less about surface blooms and more about suspended layers. Zooplankton migrating vertically at night may form concentrated clouds at intermediate depths. By timing descents to intersect these layers, mantas expand their feeding window beyond daylight hours. The glide, energy efficient by design, allows them to cover vertical distances without excessive muscular effort. Their pectoral fins operate with a motion resembling flight rather than continuous propulsion. Lift generated through downward strokes carries the ray forward and slightly upward, reducing drag compared to constant tail-driven swimming. The visual impact of a manta ray in blue-black water is profound. Its silhouette is broad and deliberate, wings undulating with slow authority. There is an eerie quality to its passage, not because it threatens, but because it appears detached from gravity. It moves as if flying through liquid sky. From a distance, it resembles a stealth aircraft banking through cloud, silent and purposeful. This image is not romantic exaggeration, but a reflection of hydrodynamic design. The flattened body reduces vertical drag, while flexible cartilage supports the expansive fins without rigid bone. Predation risk decreases during deeper glides for reasons beyond camouflage. Many surface predators rely on silhouette detection against bright water. At depth, where light intensity drops, such silhouettes become less distinct. Additionally, the manta's movement pattern shifts. Near the surface, feeding behavior involves looping turns and concentrated passes through plankton patches, movements that create turbulence and attract attention. At depth, glides are linear and controlled, minimizing disturbance. The less conspicuous profile reduces the chance of attracting opportunistic hunters. Parasite load may also influence vertical movement. In surface waters, cleaner fish remove external parasites from mantas at reef stations. However, deep glides through cooler, denser layers may dislodge or reduce certain ectoparasites less tolerant of temperature shifts. While cleaning symbiosis is a primary mechanism for parasite control, vertical migration introduces additional environmental variability that parasites must withstand. The manta, by crossing layers, complicates the life cycles of organisms that depend on stable conditions. The ocean's layered structure is dynamic, shaped by wind, rotation, and geography. Mantas often undertake seasonal migrations across vast distances, tracking regions where plankton productivity peaks. These migrations are not random wanderings, but responses to environmental cues such as sea surface temperature and chlorophyll concentration. Satellite tracking reveals patterns that align with seasonal upwelling events and nutrient influx. Within these broad horizontal movements, vertical glides add another dimension. The manta is not confined to a flat map, but operates in 3 dimensions, adjusting depth as conditions shift. In deeper, darker water, bioluminescent flashes may punctuate the void. Small organisms emit light in response to disturbance. As the manta passes through, faint glows ripple outward. Unlike predatory species that use bioluminescence for luring or signaling, the manta remains a passive participant in these exchanges. Its presence triggers reactions, but it does not generate light itself. Instead, its massive shadow absorbs the faint emissions, momentarily obscuring their source before they fade. There is a paradox in the manta's demeanor. It lacks the serrated teeth and overt aggression associated with apex predators, yet its size commands space. In dim water, that size becomes abstract, an outline without clear detail. The wings extend outward, and the head projects forward with subtle determination. Its mouth, when open, reveals filtering plates that trap plankton rather than flesh. The apparent harmlessness belies a capacity to traverse depths that many reef-associated species never experience. As the glide continues, the manta may angle upward again, re-entering brighter layers. The transition is gradual, and the shadow regains color. Surface light filters down in wavering shafts, illuminating the patterns on its dorsal surface. Yet the memory of its passage through darker water lingers. The manta is not bound to shallow spectacle. It is a navigator of structure, interpreting invisible gradients and responding with deliberate movement. In the ocean's vertical expanse, survival does not always require aggression. Sometimes it requires interpretation. The manta ray reads temperature shifts, current edges, and plankton density with a sensitivity shaped by evolution. Its deep glides reduce predation risk, optimize feeding efficiency, and align its physiology with environmental variability. The image of a giant winged form moving silently through blue-black water captures this complexity. It is eerie not because it threatens, but because it reveals a scale and depth of movement that transcends the simplistic label of gentle giant. In that quiet descent and ascent lies a reminder that the ocean's true architecture is invisible. Currents, thermoclines, and migrating plankton clouds define the boundaries within which life operates. The manta ray, gliding through these hidden layers, transforms them into pathways. It is not chasing prey or fleeing danger in dramatic bursts. It is flying through water, reading the sea as a map written in temperature and flow, its immense silhouette a moving intersection between surface light and abyssal shadow. Along the seafloor, where motion often determines survival, there are organisms that have rejected movement almost entirely. On rocky outcrops and scattered hard substrates rising from sediment, soft columns anchored to stone extend rings of delicate tentacles into passing currents. At first glance, they resemble flowers fixed permanently in bloom, their bodies swaying gently in the flow. Yet beneath this apparent fragility lies a mechanism as decisive as any swift predator's strike. The sea anemone survives not by pursuit, but by transforming stillness into a weapon. The environment around it is rarely calm in absolute terms. Even in deep and bottom ecosystems where light fades and temperature remains stable, water is rarely static. Tidal exchanges, internal waves, and thermohaline movements generate slow but persistent currents. These currents transport microscopic plankton, suspended organic particles, and occasionally small drifting animals. To most organisms, this flow represents background motion. To the sea anemone, it is opportunity delivered directly to its reach. Anchored by a muscular pedal disc, the anemone attaches securely to rock or shell. The column rises upright, composed of flexible tissue that can contract or elongate depending on conditions. At the crown, tentacles radiate outward, each lined with specialized cells called cnidocytes. Within these cells are nematocysts, microscopic capsules coiled like compressed springs. When triggered by mechanical or chemical cues, a nematocyst discharges with remarkable speed, diverting a harpoon-like thread that penetrates or entangles prey. The force of discharge is among the fastest cellular actions in the animal kingdom, a rapidity that contrasts sharply with the anemone's otherwise tranquil demeanor. In low light or abyssal settings, where chasing prey would require costly bursts of energy, this arrangement is elegantly economical. The anemone invests in location rather than locomotion. It selects sites where current velocity optimizes contact probability without tearing delicate tentacles. Too little flow and food delivery stagnates. Too much and feeding efficiency declines as particles sweep past too rapidly. The positioning reflects a fine-tuned relationship between hydrodynamics and predation. Some species inhabit vertical rock faces where water accelerates, while others settle on sediment mounds where gentle laminar flow dominates. As small crustaceans or fish larvae drift into tentacular fields, contact initiates capture. The nematocysts discharge instantly, injecting toxins that disrupt cellular membranes and nervous function. The prey's movement ceases almost immediately, not through brute strength, but through biochemical precision. Tentacles then flex inward, guiding the immobilized organism toward the central mouth. Feeding proceeds slowly, digestive enzymes breaking down tissues within a gastrovascular cavity that serves both as stomach and circulatory space. Nutrients diffuse through the body wall, sustaining growth and reproduction. This method exemplifies an abyss rule: kill without wasting energy. The anemone does not chase, stalk, or ambush. It establishes a tripwire network in water that never stops moving. Currents become collaborators, delivering sustenance continuously. The predator's role is to maintain readiness and structural integrity. In deeper environments where particulate organic matter drifts downward from surface production, anemones may supplement active prey capture with detrital feeding. Tentacles intercept larger fragments of marine snow, incorporating them into the digestive cycle. Thus, they occupy a position between strict predation and passive collection, blurring boundaries that appear rigid in shallower systems. This flexibility enhances resilience in nutrient-limited settings. The physiology supporting this lifestyle is finely balanced. Anemones are ectothermic, their metabolic rate aligned with surrounding water temperature. In colder deep waters, reduced metabolic demand extends the interval between feeding events, allowing survival during periods of low prey density. Tissue composition is largely water, minimizing energetic cost for structural maintenance. Muscular contractions used to retract tentacles during disturbance are brief and energy efficient. When threatened, the entire body can contract into a compact form, reducing exposure to predators or sediment disturbance. Predator-prey interactions involving anemones reveal further complexity. Certain fish species have evolved resistance to specific anemone toxins, forming mutualistic associations. In shallower reefs, clownfish shelter among tentacles, gaining protection while offering cleaning services and nutrient-rich waste in return. In deeper or temperate waters, similar symbioses occur with small crustaceans or fish adapted to the chemical environment. The anemone benefits from increased water circulation around tentacles generated by partner movement, enhancing oxygen exchange and food delivery. These relationships illustrate how chemical weaponry can coexist with cooperation under selective pressure. Reproduction in anemones may occur both sexually and asexually. In some species, individuals release gametes into the water column during synchronized spawning events influenced by temperature shifts or seasonal cycles. Fertilized larvae drift before settling and transforming into juvenile polyps. In stable deep environments, asexual reproduction through budding or fragmentation allows rapid colonization of favorable substrates. A detached fragment, if containing sufficient tissue, can regenerate into a complete individual. Such regenerative capacity contributes to persistence in habitats where physical disturbance is infrequent, but food supply unpredictable. The still predator also interacts with sediment chemistry. By occupying hard substrates within soft bottom environments, anemones create localized zones of increased biodiversity. Their presence offers microhabitats for small invertebrates seeking shelter beneath tentacle canopies. Organic waste from feeding enriches surrounding sediment, supporting microbial communities. Even their discarded mucus and cellular debris feed microorganisms, integrating the anemone into nutrient cycles extending beyond direct predation. One might assume that immobility invites risk. Indeed, certain starfish and fish prey upon anemones, consuming tentacles or entire individuals. Yet the combination of nematocyst deterrence and the ability to retract quickly reduces vulnerability. Some species can even detach and slowly relocate if environmental conditions deteriorate, although movement is measured in incremental contractions rather than deliberate strides. The rarity of such relocation underscores their reliance on site fidelity and hydrodynamic suitability. In abyssal plains, where hard substrate is scarce, anemones sometimes attach to sunken debris or carcasses, exploiting transient structures as feeding platforms. A whale fall, for example, becomes not only a feast for scavengers, but also a foundation for sessile organisms. As bones persist for years, anemones colonize them, converting skeletal remains into living reefs. Through this succession, still predators participate in the transformation of death into habitat. The visual of tentacles extended into dark water evokes fragility, yet the system is unforgivingly efficient. Contact equals capture. Energy investment is minimal relative to return. The surrounding current does the hunting. The anemone executes the final act. In the absence of light and in environments where mobility may cost more than it yields, such strategies dominate. As the camera lingers in blue-black water, tentacles pulse gently with each passing surge. Plankton glints briefly before vanishing within a ring of stinging cells. A small crustacean drifts too close and is drawn inward without struggle. No pursuit, no chase, no visible aggression. Just an invisible threshold crossed. In the closing stillness of the abyss, it becomes evident that motion is not the only path to dominance. The sea anemone demonstrates that patience, positioning, and biochemical precision can rival speed and strength. In a realm where energy is precious and opportunities unpredictable, the ability to kill without wasting effort becomes the ultimate adaptation. The abyss rewards those who conserve, who wait, and who transform the movement of water itself into a constant harvest. The seafloor appears still at first glance, a broad plain of sediment broken only by scattered stones, the faint tracks of passing fish, and the occasional rise of a burrow entrance. In deeper regions where sunlight never arrives, the landscape seems almost static, as if nothing could survive in such subdued conditions. Yet when the camera lingers and the eyes adjust to the subtle motion of drifting particles, a slow procession becomes visible. Elongated bodies, soft and cylindrical, move with deliberate contractions across the substrate. Sea cucumbers, often overlooked and rarely celebrated, advance like living conveyor belts over the abyssal floor. They are neither swift nor armored, neither sharp-toothed nor imposing. Yet in the architecture of the deep, they perform labor as essential as any apex predator's strike. The first impression of a sea cucumber is vulnerability. Its body lacks rigid protection. The skin appears pliable, almost gelatinous, punctuated by small tube feet that extend and retract in rhythmic coordination. But this softness is deceptive. Beneath the flexible exterior lies a network of microscopic ossicles, tiny calcareous structures embedded within the dermis that provide internal support. These ossicles, arranged in complex lattices, grant structural integrity without sacrificing flexibility. The body wall can stiffen or relax through changes in connective tissue properties, allowing the animal to squeeze through narrow gaps or resist compression. In a habitat defined by pressure and unpredictability, adaptability of form becomes a quiet advantage. Sea cucumbers feed not by chasing prey, but by processing the seafloor itself. As they advance, they ingest sediment laden with organic detritus, microscopic algae, bacteria, and fragments of decaying organisms. The material passes through a long digestive tract where nutrients are extracted efficiently. What emerges behind them is cleaner, reworked sediment, redistributed and aerated. In shallow waters, this behavior resembles plowing. In the abyss, it resembles filtration on a planetary scale. The seabed receives a constant drizzle of organic particles from above, often called marine snow, composed of plankton remains, fecal pellets, and decomposing tissue. Without organisms to process this material, it would accumulate unevenly, potentially altering oxygen levels and microbial activity. Sea cucumbers act as the sanitation system of the deep. Their feeding structures reflect this role. Some species extend feather-like tentacles around their mouths, sweeping and capturing fine particles before retracting them to ingest the collected material. Others shovel sediment directly, swallowing large volumes relative to their body size. The digestive system extracts sparse nutrients from what appears nutritionally barren. This efficiency is critical in environments where food arrives in low concentrations. Metabolism in many deep-sea cucumbers is adapted to cold temperatures and limited caloric intake. They grow slowly, reproduce intermittently, and invest energy carefully. Yet while their lifestyle is slow and methodical, their defenses are surprisingly dramatic. A sea cucumber may appear to be an easy meal for fish or crustaceans, but many species produce chemical deterrents known as saponins, toxic compounds stored within their tissues. When threatened, some release these substances into the surrounding water, creating a chemical barrier that irritates or deters predators. The effect is not explosive, but it is effective. In confined reef systems, the sudden release of toxins can even stun nearby fish temporarily, discouraging further attack. In deeper waters, where encounters are less frequent but stakes are high, chemical defense compensates for the absence of speed or armor. In extreme cases, certain species employ a more visceral strategy. When grasped by a predator, they can eject parts of their internal organs through the anus in a process known as evisceration. Sticky threads or toxic tubules may entangle the attacker, allowing the cucumber to escape. Although losing internal organs sounds catastrophic, the animal is capable of regenerating these tissues over time. The process is energetically expensive, but survival justifies the cost. Evolution has favored organisms that transform apparent fragility into deterrence. The paradox becomes clear. The animals responsible for cleaning the abyss are also chemically defended packages of unpalatability. They do not rely on intimidation through size or aggression. Instead, they cultivate the reputation of being a terrible meal. In ecosystems where energy is scarce, predators quickly learn to avoid wasting effort on prey that offers low reward or high discomfort. Chemical warfare, subtle yet decisive, secures the cucumber's continued role on the seafloor. Their ecological impact extends beyond simple sediment turnover. By ingesting and excreting sediment, sea cucumbers influence microbial communities. The digestive process alters the composition of bacteria within the sediment, promoting nutrient cycling and oxygen penetration. In regions where oxygen levels are marginal, This bioturbation prevents the development of anoxic pockets that could suppress other forms of life. Their movement effectively ventilates the upper layers of sediment, maintaining conditions suitable for worms, small crustaceans, and microorganisms. In shallower tropical reefs, sea cucumbers also contribute to calcium carbonate balance. Some species ingest sand rich in coral fragments and excrete processed grains, influencing sediment texture and distribution. On coral reefs where erosion and growth must remain in balance, their activity subtly shapes substrate stability. In the abyss, the scale is broader but no less important. Over large expanses, thousands of individuals collectively rework the seabed, ensuring that organic input is redistributed rather than concentrated. Reproduction among sea cucumbers reflects adaptation to unpredictable environments. Many release gametes into the water column during synchronized spawning events, often triggered by environmental cues such as temperature shifts or lunar cycles. Fertilized eggs develop into planktonic larvae that drift before settling onto the sea floor. In deep-sea species, reproductive strategies may differ, with some brooding young or producing fewer but more developed offspring. The variability underscores an overarching theme: survival in the deep demands flexibility. Thermoregulation is largely passive, as sea cucumbers are ectothermic and conform to ambient water temperature. However, their metabolic processes are fine-tuned to cold stability. Enzymes operate efficiently at low temperatures, and growth rates reflect the slow pace of abyssal life. In this environment, patience is not a strategy, but a necessity. Energy must be conserved, and sudden changes are rare. The presence of sea cucumbers often increases following major organic falls, such as the descent of a whale carcass. Initially, scavengers such as crabs and fish strip the soft tissues. Over time, as decomposition progresses and sediment becomes enriched with nutrients, sea cucumbers arrive in greater numbers to process the surrounding substrate. Their involvement marks the transition from dramatic feast to sustained recycling. They are the final custodians of what once was a massive organism, converting residual material into the baseline productivity of the seabed. There is quiet irony in their appearance. Their forms lack the sleek contours of predators or the elegance of rays. They resemble inert objects more than active participants in ecological drama. Yet the abyss is maintained not only by those who hunt, but by those who clean. Without sea cucumbers and similar detritivores, organic matter would accumulate, altering chemical gradients and potentially destabilizing benthic ecosystems. The sanitation of an entire world depends on these slow, unassuming bodies. As the camera lingers on a single individual gliding over dark sediment, tube feet pulsing gently, the scale of its influence expands beyond its size. Each mouthful of sediment processed, each stretch of seabed aerated, contributes to a system that supports countless other organisms. The deep ocean, often imagined as empty, is in fact sustained by this continuous reworking of material. The poison broom of the deep does not sweep with dramatic gestures. It advances steadily, transforming decay into continuity. In the stillness of the abyss, where dramatic hunts are rare and light never penetrates, maintenance is survival. Sea cucumbers embody this principle. They make themselves undesirable to predators through chemistry, protect themselves with regenerative resilience, and devote their existence to processing what others leave behind. The result is an ecosystem that functions not because of spectacle, but because of relentless, understated labor. In a realm that can seem inhospitable and barren, life persists through balance. And beneath the silence of dark waters, where carcasses fade and sediments shift, it is the harmless-looking custodians who ensure that the abyss remains alive.